local things. So today we have a general thing. Only next week I want to do the other one. So I think you are welcome to continue. If you want to start, I couldn't hear all. See, I could hear partly what you were talking, you and Wenzong, but I couldn't hear. Was there anything else important?
No, I think we've covered everything. You're basically up to date.
Okay. There's one more thing I just want to,
we are live now, by the way, Rajan. We've already gone live.
Yeah. So okay. One more thing, just want to share with you, and then we'll talk about later. There is a possibility next end of May 2025, I may be able to come from New York to Europe, for a week or something. So we can figure out where we should meet. And Wenzong is already in England, so he may be able to come. Only few people cannot come, but we can do always live chat to those people who are like Manuel Malaver. I don't know whether he'll be able to come. Emery, he may be able to come, but because
Emery's in the US though. So
yeah. So he may be able to come.
It's easier for you to meet up with Emery where you are rather than meeting him up in Europe.
Yeah. So, but I will try to, we can probably come, and I like to have a, in-person thing, so we can start that process, and then So we'll try to find a venue and thing. We kind of went through it earlier, Christopher, but we can start researching. And if you find some place, let me know. That's or we can talk about it. After next week, I'm going to present that, and then after that, you can. We can talk about that.
You want to do a live conference, is it? And
yeah.
Oh, okay.
Yeah. So people will know what you are planning. I mean, we can probably talk confidently, and then we can, put live and.
Well, I can host it in the university here. Yeah, or maybe at Queen's University.
Or we also mentioned about some place.
We could also do like a hotel or something,
Yeah, and Ireland is one place, but there is another place we were considering before. The Benelux countries.
Luxembourg
or something. But we have to find out. Yeah, where.
We should probably find. We're looking for like where's the place with the best value to fly to.
Yes, exactly.
And then also, but then when you get there, where's the best place with like the lowest sort of costs of living?
The very important, because there is a very limited budget, so we have to ensure like Airbnb maybe, because if we share, maybe it's okay.
I don't know. Actually, is Airbnb cheaper than?
Or we have to do something else that you do there. You probably know a lot more how to reduce the the cost in Europe.
I'm not really that well traveled or whatever in terms of like Airbnbs. I think I've been in like maybe 2.
Now it's costlier now because everybody is using. Yeah, you are right. So it's quite expensive. So we have to find that probably a tent or something.
We can work that out later. Those are the kind of details. But I think I'm on board anyway. Although it does depend, like if I have other conferences to go to during the summer, like there can't be too much overlap, and they can't. Well, there can't be any overlap, but if they're too close together, I might not have the.
I see.
Because like I'd have to put so much energy into like one conference, I wouldn't be able to do the other one kind of thing. That happened to me before, so stuff like that we need to just make sure that they don't overlap. And I'm sure that's true for everyone else, obviously. So, but even so, even if I could still meet up and and just a kind of holiday kind of vibe rather than a work vibe.
Yeah, it's a combined thing. Actually, we will combine. That's the idea. We'll combine both whole days. So we can like 1 or 2 days of very important topic, and we will live stream and everything. But the other few days we can do like a holiday type of thing. We go around. We have some kind of a camp or some look places. So we'll travel.
Okay, well, we'll talk more about that another time, because I'm sure there's loads of technical details about cameras and all that sort of stuff. So it sounds interesting. Yeah. Okay, so for this week, well, we have well, two bits of news, I guess. For a start, we have Wenzong back with us. So if I go back into into here. So so yeah, so we have Wenzong with us, who was a researcher. How many years ago now was it, Wenzong, that you were on with us? Probably 2 years or something like that.
You mean I left my previous job?
No. You came on and you did a presentation for TEGS about, I think it was maybe 2 years ago, or maybe
2 years ago. 2 years ago. Yeah.
Oh, okay, cool. Yeah. And that was on like mainly on the topic of tired light theory, correct?
Yeah. I developed 3 methods, different methods, to prove, the light will, tired, will lose energy during propagation without blur the image.
So what image are you talking about? Like, where are you talking about telescopes or?
Yeah, because originally they, when they proposed the tired light theory, actually earlier than the Doppler shift, the space expansion.
Oh, really?
Hypothesis, yeah.
Oh,
yeah, they proposed, the tired light almost the same time, only half year time difference.
Oh, right. I had no idea that it was that they were so close. But
that very close.
Because, like, why would anyone come up with the tired light theory like long into the proposal of the Big Bang and the expanding universe, when that has become so sort of central to all of cosmology, for better or worse? It would be so hard to like sort of shift that from its pinnacle at this late stage, I think. Although that shouldn't be the case, but why would people even feel it necessary to come up with a new theory like tired light if there was nothing wrong with the original theory as well? But obviously we know that there are problems with the expansion theory now, especially with the results of the JWST, which is because I think they recently found galaxies that are older than the universe, which is a major problem for the theory of the Big Bang. And so therefore, I mean, obviously some new explanation is needed. So either the universe is not expanding, which would lead into your kind of tired light proposal, or I think you had super photons at one point, and then I think you changed that for something else. But or equivalently, kind of my theory, where we have a 4-dimensional hypersphere projected onto a 3-dimensional tangent space, which would also produce the redshift, but no expansion in that model. So they're two kind of very different ideas, I think, but equivalent in the sense that they both account for redshift, but without expansion. So that's really interesting. And Wenzong has some new research that he's just published with the Canadian the Journal of Applied Sciences, the Canadian Journal of Applied Sciences. I think that's how you say it. And so he'll probably talk to us about that. Also, and just any other news, if you want to catch up with us, Wenzong, you can do that. Okay, so before we get into that, we're gonna return to the research that we looked at last week, which is in here. So last week, if you were with us, you will recall that we were kind of going through Well, I think we went through a number of different topics last week. It was quite hectic in terms of the amount of information that we were trying to absorb. It gets quite stressful, but at one point, I think it was towards sort of the end of the live stream, we started looking at the symmetry group SU5 and its embeddings in the standard model. And I don't think that I got the chance to mention it at the time, but what I was going to say was that all of that research that we were looking at comes from this book called by Walter Grainer, I think, and Brent Muller, called Gauge Theory of Weak Interactions. And this is the 4th edition. So you can sort of scan down through this. Now, I've actually read this book. So I don't know what date of publication this is. What did we?
You mentioned the 2009.
Oh, is that what it says? Okay, so 2009. Wow. Yes, you're right. Oh, but this is weird. So it was published before in 1993, 96, 2000, 2009. Because you see, I've read this book. Oh, wait a second. Duplication of this publication. It's a copyright law. See, that's weird because I have read a copy of this book that was published in 1970. But it had, the same title, I think, and the same author, but all of the contents in the book are different. So you might say, well, how is it the same book? It was the same title, same author, and yeah, it covers like a lot. Like some of the chapters are the same, but pretty much all the chapters are different. But some of them are the same. Like, and the kind of feeling of the book is entirely the same, and some of the pictures are the same. So I'm pretty sure it had this chapter all about the Higgs mechanism, which is very interesting. And then it goes into the Yang-Mills field. But in the version that I read, because it was written in the 70s, they still didn't know, like, they were discussing the Yang-Mills field, but obviously it must have been quite a new theory because it was only able to deal with massive particles, I think, but not massless ones, something like that. And so there was this whole section was just the author kind of saying, well, we don't know if it's right, but how would we apply it to this problem, like, of massless photons, if it did happen to be correct. Actually, it was this section, same chapter name as well, the Feynman rules for Yang-Mills theory. And it is interesting because some of the sentences are the same, but they've obviously edited out all of the sections to do with the Yang-Mills theory potentially being wrong, because, well, presumably at this point, I mean, Yang-Mills is basically everywhere, isn't it? Within the standard model is connections to, I think it has connections to the strong force, the weak force, obviously electromagnetic force. So I think it's fairly well established, and so this whole book has been revised, but it has been revised to the extent that it is no longer the same book. So it's a bit like, that the house that Jack built or whatever. At what point do you say it's a new book and maybe stop saying it's a reprint? And another thing about it, when the original book that I was reading, I was kind of going through all of these sort of, I don't know what you call it, algebraic, equations and stuff. I'm trying to wrap my head around them, but I was, in particular, like things like this. But I was, I guess what I'm trying to say is I was lacking certain pieces of information. So while I was able to follow along to some degree, I was really, I kind of struggling in some respect. I didn't get a whole lot out of it, but also I note that this is much easier to read than the original book. So the original book was just very, very technical, and this one seems to be a lot less so. But also, I have the added advantage of actually understanding a bit more of the equations and stuff like that, so that helps. Now, by the way, this is not a presentation, so the purpose of this is not like me kind of up here solo discussing this. Rather, we're going to go through the bit like we did last week. Go through the some of the equations here and the different sections in this chapter on unified gauge theories, symmetric group, SU5. Of course, I will be reading sections of this, and much like we did last week, we'll just try and interpret it and see how much we can understand. So yeah, at any point you can jump in, ask questions, ask me to repeat something or move to a different page, or just share your opinions and insights. Of course, Rajan, you were a great help last week, I seem to recall.
Oh, thank you.
Yes.
Yeah, I just want to let you talk about it, so that, and until you reach a point of the thing that we can,
yes,
we can break that, and then, and then probably go in a different direction, using our questions or queries, like a discussion. We can go into that, but yeah. So, because you present, you have done a lot on that. I have done some of it. And I can tell you the following. I agree with you about algebra, and I also get, trying to wrap around the mind and trying to figure out what they are. Yeah. Of course, I don't have complete math background in that, right, in the way they're doing. But also, I'm very skeptical because the math, yeah, is overwhelmed. The physics. So where is the physics? Is hidden there. But on the other hand, I myself did abstract. So I have published. I will show, probably not today because you and Revenzong, but maybe next week after I present following that. Because there are a couple of papers already, one of them already published in the astronomy, one of the astronomy journals, and it's very important. And now, see, the fourth thing, we already talked about it.
Rajan, is that a paper of yours that's published in an astronomy journal, or?
Yeah, it's open access journal of astronomy. It's fairly good.
That's cool, but I didn't think you really did a lot of astronomy, do you? Or what's the subject?
Well, they published that because it applies to astronomy. It's actually physics, the quantum physics that applies to, the time and everything. But it goes further than that. And the main thing about the clocks and things like that, it will be useful for, it's just setting up the stage where actually you put a clock on the particle versus clock on the galaxy. What will happen? I mean, to tackle that, you need this background, So essentially everything comes to a clock because, in one particle, the clock may be running very fast. The other particle, it may be running slow. And in dark matter, the clock may be frozen or the clock may not exist. The question is when time exists, when time doesn't exist. The dark matter, there may not be any time. Things like that, to tackle that. That's where the abstract aspect is. What I'm saying is that the abstract has usefulness, the math. And then I derive from that abstract. So it is useful, and I think Revenzong also did very similar in a different direction. And he has proved about a connection between the Planck's constant and the Hubble constant, right? And so, and he has found some interesting things from there. And for you, Christopher, you have found from the space aspect, and then the group theory, and you have put together something of your own. Where it reaches certain fundamental conclusions about the tangent plane and everything. It's your model, but I think it has some, it has usage. So we can put together all these, my feeling, I am coming from the time side, you are coming from the space side, and then Menzong is trying to put these, the micro and the macro together in terms of the constants, which Christopher or everybody is talking about. So all these are now pieces of the puzzle. I think, I say any puzzle solver, you have piece of puzzle, but sometimes there is extra puzzle, there is not enough pieces. And then when you put together also, they are not, sometimes they're easy, sometimes they're not easy. Sometimes they are completely solvable, sometimes they are not completely solvable. And quantum gravity is one such thing. But I still think that, I think those things are sitting the right way, because you see the string theory. I was thinking about string theory, which is one of the most abstract theories and beautiful math, still very useful. But there's the question is, there are many string theories. The Swammland conjecture says that there is no global symmetry. There is no global symmetry because the gravity has only local symmetry, not global symmetry. So what creates the asymmetry? I was thinking. So before I stop at this one, that's my most recent one. I'm thinking aloud now, is that actually the direction of time. I mean, actually, I prove in one of the things about the direction of time things are very important. The arrow of time, which we think is entropy. What is entropy? Things like that. I'm touching upon all that. But so in one direction, you have one direction. You have the gravity, and the other direction is the time. So we have to talk about Noether's symmetry. I think applies in general to all of them as far as physics is concerned. Although we don't know whether it breaks, it does break symmetry at some point. But the key thing about the asymmetry may be that the time, when the time comes, like superluminal thing, but you're talking, there is no time. So with the hot PDP mechanism, things like that, that's one of the mechanisms I think is reasonable, quite reasonable, can explain. And the particles come. When the particles come, immediately the time comes. There's a clock on the particle. So the particle has certain, the clock runs on the particles. Some particles stay there like partons. They may die off. They may have very short time span. Some other particles like proton, everything, they have very large time frame. Like electrons, they are in the universe, the same as the universe. But other particles come on and then they die out. So there's annihilator and generators and annihilators, right? So like positron, electron, they come together and they annihilate. But they are separated by space. So I'm actually coming up eventually, maybe a couple of months after I publish these 4 papers, very important reference frame. So measurements, where is the measurement problem? It's a question of reference frame. So that one paper will concentrate on that, how to really choose the right reference frame, and are we choosing right reference frame? I think there are problems in the reference frame that may be the problem, that in the measurement problem. When you measure, we are measuring something that is not congruent to what we are measuring. So things like that. And also, very simple thing is that in mesoscopic level, we can easily measure, for example, length and things like that. Your standard measurement, we can use a ruler, but we cannot use that. What you call the measuring rod, we cannot use that when you go into astrophysics or quantum physics. That doesn't apply. We cannot use that. So the actual measurement aspect changes depending on where we are. Mesoscopic level, we can measure it, and the time we can use clock and things like that. So we have to change the references. So very important. And
Right.
finally, the question of signal. The information we get from astrophysics is the signal. So we have to find a way to process, manipulate that, and then use an abstract way to, without assumptions, use that signal and convert it to temperature and the things that we can measure. So those are the main things. What it means is that the gauge theory, things like that you are talking now. I mean, abstract things are important. Like you are saying, the commutation relations, things like the commutativity, right? And the
Right.
non-commutativity is important. because it seems like the gravity is non-commutative. I mean, from that point of view, and the other part of is the time. So time and gravity somehow are providing some kind of a symmetry, and that symmetry is automatically asymmetry because gravity works one way and the time works one way. So there is automatic asymmetry. Time says, I'll keep going. So that's how the matter is produced. Gravity says, okay, it pulls back, and then it tries to create black holes and things like that. So these two are working, but they are working in such a way that it creates a real universe. So that is the trick. I think that gives, because if you just say finally it's positron, electron, they annihilate, and then there won't be anything existing. So how do you describe the asymmetry where from the whole origin of the universe and continual evolution of the universe occurs? So that is a fundamental question. It's a philosophical also, but also I think finally boils down to the proper physics. So that is where the abstract concepts are important, but you have to pull out something. See, it's fine. All these equations are fine, but what are you pulling out? What is the gauge theory about? Why is that gauge theory? I think it's not very clear. Gauge theory is a way of measurement. So gauge theory is something that helps, a theory that helps in the measurement. Very simply put, very loose term, but very important, because we have to, whatever equations we come up with, we have to pull out some parameters, something that we can measure. Eventually, that's what is important, right? If you say field, you should be able to measure that field, but measuring that field requires a proper reference rate. So those minute details are important. I think we are concentrating on that, and it's very very appropriate, very important. Although they are very, like you said, very cumbersome, very painful, and very mind-boggling, I think those are quite important. So I think we are in the right track of concentrating, because we don't want to, there are even trivial things I am considering, trivial solutions. What happens in the mesoscopic level? A lot of things, time becomes trivialized from the time tensor that I'm talking about, get trivialized. That's what we are measuring. So they have limited usefulness. They're still useful for measurements. But then these theories are so up in the air, like the gauge theory, we can track, like they're talking about the matrix and things like that, matrix operations, that are we pulling out something that we can measure? Like a lot of things we are not able to measure, like Higgs boson is the only one in the weak theory, right? Higgs boson is the only thing that is the standard model that was measurable to a large degree, and that proved. And then of this Salam model was the one that is most useful. And you mentioned about Yang-Mills. I think that's important thing to concentrate a little bit on, like 1 minute or something. The Yang-Mills, what I was thinking is that is there everywhere, yes, as you said. But the mass gap problem is one of the big things that came out of the Yang-Mills thing. So they're trying to describe how the masses. I mean, I don't know whether they are. See, that I'm not sure. Are they describing how the mass comes from the field, right? So let's say there's a Higgs field everywhere. I'm not sure that that's the only one, but let's say Higgs field everywhere. How the masses come? This is what idea Higgs boson. How the masses come out of that field. So if there is a wave, how the masses come out of the wave, so to say. If there are Sitterbaum gun or cosmic microwave background or waves, things like that, or there is a general wave to start with, how the masses form from that wave is, I don't know whether they are trying to tackle that, and the gauge theory helps in that, but we are not seeing any direct connection from the physics point of view. See, I look at from the pure physics point of view. The other side is abstracting. So one side is coming from there, one side is coming from there. When they join, are they making sense? Like the quantum mechanics and the relativistic mechanics. They come together, there are problems. So in the same way, in a more general sense, the mathematics come from their side, physics come from this side. And you have either physical mathematics or mathematical physics. Are they really solving the problem? Are they able to come together on the same level, on the same page, and make sense to us? So finally, it has to make sense to us. And I believe it can. See, some other people may debate and say, okay, that's the way it is. You have to go up there. You have to be trained to that. Your brain has to be trained to that, and then you will see it. But is it that way, or that we are normal? The way we are normal, like we are looking at the light or the sunlight, and we are daylight and then night, and we are able to differentiate that. And from that point of view, we see stars. From that point of view of the perspective, can we explain all those things in that perspective? That's see, Newtonian mechanics was useful, and it was still successful, and Galileo is because they were able to describe those things. Although there are problems in the, there are things that you have to improve. That's why quantum mechanics and things like that came. Like ultraviolet crystallography, vacuum crystallography, things like that. The thermodynamics was the one that was supposed to glue together all these things. But unfortunately, the catastrophes, made it difficult for the thermodynamics to describe everything at the small level as well as later level. So I think that's the crux of the thing. So whenever we are discussing this, we should keep this in mind, at the back of our mind, so to say, that are they addressing that thing? Is the physics coming out of it? I think it's like Sabine Hossenfield is always, I think, the right things to do, looking more critically into that, and we should produce into that. What exactly is the Hermitian matrix do? Things like that. We should be able to describe that in a sense that all of us should be, we are, like I am not that deep math, but I think I have enough math for the physics. Just enough math, and I feel confident about that because I was able to derive things. But these things doesn't make sense to me a lot. I think that there is like you said, there is something missing, some explanation missing here. That's the problem with like a GERD or GERD. A lot of things are understandable, but there are things very abstruse. I may be same with my thing, but I'm trying to break it into such a way that you can connect with the very simple algebra, geometry, and everything. I think, Christopher, you are trying to do that. Wenzhang is trying to do that. But again, there are a lot of areas we don't understand completely the derivation aspect of all of our things. I think that's where we should eventually go. And this one also, going through that is helpful. Because gate has become one of the most useful things. And I believe eventually M theory, that I'll talk next week in the history of physics. Because the history of physics is, if you look at the episodes, that's one thing useful because it doesn't go too much math, but it does describe what's the progression of the physics. So it's very useful for anybody to go through that. And when we have the documentary movie, again, that will be one of, like Oppenheimer. It will be something that everybody, people who does not have much background in physics or math, will be able to understand some main concepts. And I think that's the main thing, like how to make into normal physics all these complex things is where you take out, you try to distill it and find out what is the underlying principle, what is the underlying physics. And that physics should be explainable. And I believe that you can connect with the mesoscopic examples, like I have done a few, and I still have to do a lot more. I believe that's how we get to see. If you look at that, how is our mind working, the consciousness, things like that. How is it working? So it is trying to sense or observe or trying to find a deeper thing inside, but still it's connected with our body, and that's where the consciousness comes. So we have to be able to, if you look at different angle, we have to put them together, but we should be able to explain that. Of course, the whole thing, like I said, transform, it's a black box. So that is something we have to keep in mind. So the whole universe still may be a black box, but we are looking at different point of view, and that point of view, we should be able to explain it in such a way that, in general, should be explainable. And that explanation is lacking. I think that's the main thing. Like they have come up with this book, Unified Gauge Theories, but I think what is lacking is that what is the physics, the underlying physics in these things. At each point or each chapter, they should come up with a very one-page statement or explanation of what that physics is. And that should be, without going to the math, that should be self-explainable. I think that is the key thing. That should be explainable without referring to, this gate, this subscript mu, things like that. You have to take out the symbols mostly, also expand the symbols, explain the symbols, what they stand for, what it is for the physics. I think that is what is lacking. And that's what's making us very, very difficult to understand the physics. So we are breaking our heads over it. But brainstorming does help, like we are doing now. But I think we should keep in mind there is something missing here, like the missing mass problem. And that should be one of the central points. If you have a web structure, that should be the main thing, and then we connect with our own theories or what we develop. I think they are all useful. So I'm looking at for a different point of view. I look at them as most of the theories as components of a puzzle or a piece of the puzzle. But does the piece of the puzzle come together to form a grand unified thing? Is still up in the air. Like quantum gravity, things like that, maybe one puzzle, but we put in the puzzle, for the puzzle, we have to have something that a descriptor for the puzzle, like quantum gravity, maybe a good descriptor. That itself, we have to justify why it's that. So once we are sure about that, then we see, okay, all the pieces of the puzzle, can we put them together to produce that quantum gravity thing, which will eventually do grand. I believe that's possible. We are not there yet. And I have more and more reasons to believe that, it's more and more feasible. So that's the way I look at it. So this one, for example, when we say from these we construct Hermitian matrices according to the prescription, whatever that reference is, right? I believe what is missing here is right there. When you have that matrix, there should be on the side or something, some small explanation of what that Hermitian matrix is, very simple way, and what property might the main property that's used, and why it is what is necessary condition. Without going, we keep going back. Again, we are diverging. Again, we are. So that small note will help us, because we know in general we are reading through that, understanding it. Maybe we are not spent too much time calculating it. You have to do some calculations, but it should be self-explainable. It is not, actually. The diagrammatics are the following form. It's okay. Why is that? Why is C11? What is the connection to the earlier matrix? How did you derive? Yeah, that's the whole question.
So yeah, I mean, there is, it does kind of speak about that up here, when it's introducing, I guess we just passed it. It's this, but I know what you mean. Yeah, because that's what I was saying. Last week, it was great to have your input on this, because you were catching things that I would sort of just gloss over, because either because you'd have a good handle on the matrices and that line of things. So it's good to have your input on the process. But I believe it's something like to construct n-1 linear independent diagonal matrices, it is common to form n-1 linear combinations of. So this must be the constructor kind of thing, as follows. So these seem to be the matrices here. So we have minus plus minus plus. The commutation relations. Oh, sorry, of the matrices C hat A B are these. So okay. So it is interesting. You know, we have the you summing over sum the matrices. Or in matrix notation. I see. So you're saying commutation relations. Are they commutative? So I mean, is this not a when you have that little curly D? Is that the delta, the Kronecker delta, or something?
Yeah. Yeah.
Okay, so the Kronecker delta times whatever matrix. Oh, and the indices are reversed on each one. So so you'd be talking about the diagonal and the non-diagonalized version, because the Kronecker delta is just going to give you back what the identity matrix kind of, or the you know, the space-time metric of -1, 1, 1, 1, 1.
Yeah.
But I think we could probably move past this. So
yeah, I would think that for commutation, that bracket, Dirac bracket or whatever, a Pauli-Dirac bracket has to go to 0. I think it has to go to 0 for commutation. I have to check that.
Right.
Equation 911
yeah.
or 910. It has to go to 0, I think.
So yeah, it's A times B minus B times A kind of thing. And
yeah, so they're equal. Yeah.
Right, okay.
You can commutate. Yeah.
Okay, so they are saying that they are commutative, but I believe this is non-abelian. I'd imagine it is anyway. Well, it must be, because SU2 is non-abelian, SU3 is non-abelian, I think, and since both of those are subgroups of SU5, that means SU5 is also non-abelian. Now we get into, so it seems like these C hat AB matrices, in the case, so they generate these U5 generators. So we see 2, 4 just means row 2, column 4, right? So we get a 1 in there. So that should explain all of these. So C1, C11, sorry, would be just what? This. That would.
The rest of them will be 0.
Yeah, and everything else is 0, correct? And so then they're saying that. So then there'd be linear combinations as well. I think they're saying, because right. So because we looked at. Wait a second. How far are we into this already? No, just at the beginning. Huh. So it could be that we're skipping over important things, but at the same time, you know, so it's good to have a handle on the basic fundamental setups of things. Oh, here we go. So you can have linear combinations, which just result in matrices like this. So
you can see what you said is good, because that 1 appears in that place, and because C2 4 and C4 2 is the other place. So
yes, so that's easy. It's easy to comprehend. Okay, so that's another point. You know, it's good to have a grasp of the fundamentals, but sometimes we also don't want to get bogged down in those if we're not going to make any headway, or if it's too simple and we're just overthinking it. Some issues I have are like, what is the reason why it's 1 over -1?
Yeah.
Like, where does that come into it? So here we have C11. We mentioned that, and to C55. So those are diagonal matrices. Well, I wonder why. Just because the 1 is lies somewhere on the diagonal.
Yeah.
Okay. They are Hermitian, and there's 25 of them. In order to construct the generators of the SU5 group, we form new diagonal matrices that have 0 trace as required. So, so this is the one they want to construct, presumably equals. So what is the 1 in the stylistic notation here?
all the ones are there.
Oh,
the,
is this? You think?
Yeah.
Oh, yeah, that makes sense because this is this, and then that is that, right? So this is the identity matrix. Yeah. Okay, I haven't seen that before. And then why is it -1/5?
Yeah, that's the thing. I mean, there is a calculation they're doing. They're not describing. That's what I'm saying. There's a missing explanation. They're doing some calculation earlier, which shows that when you do that, you have 5 of them. So you have to
find the unique here, Rajan. So using so we might have to keep going back, but I think right. So you pointed out last week where the matrices. These are the commutative, maybe, and then this group are Hermitian, right? So they're creating some Hermitian matrices using these terms, since
the fundamental basis is the polymatrix. They use a polymatrix.
What, the adjoint matrices or the Hermitian?
Yeah. It's the polymatrix, which is the complex conjugate or something like that.
Right. And that equals to the other one when we take the indices the other way around or something. Although I'm not sure, how can you take indices the other way around? So there's, so instead of reading from A to B, you go B to A, so it would be down here instead or something, just like where we had here 2, 4, 4, 2. So they're
4, 2,
right. So they're kind of Hermitian, like the adjoint version, and then same with the this kind of complex version or imaginary version. Okay, so that seems reasonable. They also seem to have addressed the other point that we were making here. So using the linear combinations of 9.5, which is those, we can alternatively employ C hat AB, where AB is 1 to n, as generators of U1. In order to infer the corresponding generators of SUN, we require the matrix CAA to be traceless. This can be achieved by subtracting a multiple from the unit matrix. So there's the unit matrix, or these are the matrices we're interested in. We subtract a multiple. So this is the 1 divided by n.
So it's 1 over n times that.
And this is SUN, so we're in SU5, so they put a 5
in there. 5.
Right, times the identity matrix equals this times this. So it's the sum from 1 to n. Okay, so it's summing over the matrix, over all the indices of the matrix, correct?
Yeah.
And then, so that must be what this result here is then, where they're just...
The elements,
they sum over the elements. Yeah. So you're not getting a scalar out, you're going to get another matrix, which is, and it's going to look like that. Okay, and so on. Choosing linear combinations.
Oh, that makes sense. Why? If it is not scalar, so it's non-commutative, probably. If it is not scalar, if you don't get a scalar result, it becomes non-commutative.
Well, when I see like a summation, I'm thinking, all right, we're going to get a scalar out, but clearly not, because you're summing over the indices.
Yeah.
And that's, so sometimes, I mean, that's quite obvious, but
you still get a matrix.
Yeah. So, and then we have another one. So this looks to be the same kind of thing. And then we get the results out as well.
There's a simple reason. Matrix intrinsically is non-commutative, right? If you have matrix, intrinsically they are non-commutative because the order matters. You multiply one matrix, A matrix.
Yeah, that is true. Yes. I mean, there's certain ones that are commutative, right? Like in a group, you could have some matrices might be commutative, but other ones won't be. So, for instance, the identity times anything will be commutative. Okay, so, and then there might be a few other ones as well.
Yeah.
But I'm not sure. So here we have 1 divided by the square root of 15. That seems to just come out of nowhere, and also this all being times the square root of 3 over 5. I don't see where that has been defined, predefined. But that could be to do with coupling constants or energies that are.
Yeah, see that that I'm saying that explanation is missing there.
Yes, but this could be. Well, let's see. Let's see if they. Yeah, they didn't mention it. So I think this might be to do with coupling constants or something from the standard model.
How did they get 916, equation 916? That you have to go back to, do they say how they are getting the 916?
Okay, well, we'll read this. Choosing linear combinations as indicated in 9.8, which I think we already saw was that. Oh, okay. So these are the linear combinations they're talking about. Okay. We obtain 4 linearly independent matrices, which are normalized such that. Oh, so maybe it's a normal. It could be a normalization.
Squared. Oh, the traces of the squared matrix are equal to the squaring. Then they are taking the root. First they are squaring it, and then they're taking the root.
Here, right? Oh, so the squares matrix are. Oh, that's a bit weird, though, isn't it?
Yeah.
So, because like this is not traceless here. Oh no, well that's traceless, right? Because so
they add to 0. Yeah, they add to 0.
Oh, but wait a second. This here is also 0. It's not equal to 2.
See, they are doing. See, the first one is traceless, right? The second one, 1 over 5, that also is traceless, right?
So
but when you add that together, they're not traceless. Oh, they are still traceless. Yeah.
Yeah, it's still traceless. And this one, traceless. In addition, there are 4 times 5 equal, right, 20 non-diagonal generators. So that altogether we have 24 generators of the group SU5. Okay, so we have 20 of these non-diagonal generators. Because presumably these are the diagonal ones. So 1, 2, 3, 4. And they said there would be 4 of these. So these are the diagonals. And then the non-diagonals would obviously be like 1, 2, 2, 3, 2, and all the rest. So there'd be 20 of those. And that gives 24 for the group.
They're only multiplying that by square root of 5 over 3. And when you do that, the other side has already 1 over square root of 5, right? That's how we get 1 over square root of 150. When you do that, 1 over square root of 115. But the equation 916, on the left-hand side, you have square root of 5 over 3. That's one. How do they get that? And they're multiplying it by that Hermitian whatever matrix. Why is it square root of 5 over 3 they're multiplying by? That's the only thing. Then the other one will make sense. But that's...
Okay. Okay, that's an interesting point.
Where are they getting that square root of 5 over 3?
Yes, I don't even know how we'd go about searching for that in the document because...
It's squaring and taking a square root something. They're squaring and they mentioned somewhere the square of the matrix, the trace and everything a little bit earlier.
Okay. Well, what we can do is we'll just what I tend to
go through that, and then we'll come back to it.
Yeah, good idea. Okay, so the kind of thing that we were looking at. So here we got the Casimir operators, sum A, B. So here's a summation. Now this, right, okay. So we kind of looked at that already. We're not going to go too deeply into this, I don't think. What we did get to before was the irreducible representations of SU5. And they say it's convenient to use Young's diagrams. I debate that, but maybe they're right. But off they go.
When anytime you feel that you have an explanation, please jump in. Thank you.
Oh, yes, absolutely. Yeah. So H1 minus... So this looks very similar to what was going on earlier. But okay, so basically we get to the irreducible representations. Now we went through this before.
Yeah.
I know that we understood this part, and we got the sense. Well, basically, we figured out that these are just permutation. What do they call them? Conjugate representations or whatever. So that's fine. So we understood all of this basically by bypassing Young's diagrams, which is unfortunate because a lot of this research is based on Young's diagrams. But however, I think we can get by using a lot of this. So here's the 24. So that was they're all the diagonal and non-diagonal matrices plus 1, which is presumably this. So so we've covered this. So we kind of have a good handle on that. So we can move on to the embedding, which we might have gotten to this point, I think. So we have the SU3 color charges times the left-handed, weakly interacting leptons and quarks times U1. And this U1 is the weak, what is it called? The weak hypercharge?
The generator, right?
Yeah, but it's not to do with the electromagnetic force. It's the hypercharge. So that's strange. So basically, this grand unified theory, which is trying to put them all into this SU5 group, is the smallest semi-simple unitary group incorporating all gauge groups of interactions, is only covering the SU3, the weak force, the group of weak isospins of left-handed particles for SU2L, and the gauge group U1 of the weak hypercharge. So, and it's important to note that this is also only dealing with the first generation of particles. So it's quite limited in a way, but it's also pretty good at what it's doing. So even though there are problems that, as we'll see later on, with proton decay in this model. So, okay, the color group SU3 is completely blind with respect to weak interactions described by the Glashow-Salam-Weinberg group. So this is basically the weak interaction. So we have when U1 hypercharge times this SU2L, and then you have the whole Higgs mechanism, and then out drops the symmetry breaking, which is the heavy W bosons and Z boson, and the massless U1 electromagnetic photon. So that's all that's doing, really. Now, I have a bit of a problem with SU3. I'm not sure if SU3 should even be used, but so we'll just overlook that and say it's a placeholder for. So you could have lots of different groups instead of SU3. So, but we'll just go along with SU3 because it's used here, and we'll try and stick to what they're doing. Consequences of these considerations built into the theory by reserving the first 3 rows and columns of the 5-dimensional representation SU5 generators for the color group SU3, while the last 2 rows and columns are assigned to the weak group SU2L. So basically what they're saying is these 3 will be the SU3, and then down here will be the SU2L group, and which means these are reserved for other things, which are like products of these 2 or something. Or okay, so this arrangement completely specifies the structure of SU5 and determines in which way U1 is incorporated into SU5. So U1 will be, strangely enough, it will just be the diagonal part.
Diagonal.
Yeah, I believe so. As we shall see, this enables us to calculate the Weinberg angle from SU5 and exhibits that the postulate of a unified gauge group SU5 is more than just a mathematical rearrangement. It contains physical predictions that can be tested in experiments. So that's important. The diagonal generators of the group SU3 in a bold there, which means as a subgroup of SU5, are constructed from the diagonal matrices, these which have zeros in the 4th and 5th columns of the right. So there's none of this SU2 is going on in this SU3 subgroup. So it's really just restating what it said before. Since the generators of SU3 are required to be traceless, we form the following combinations. So these must be the generators for the SU3 group. So they're really just doing everything in a quick shorthand way. Now it's divided by a third here, presumably because of the charge or because of the way that the SU3 groups are constructed. They have this times minus 1 over square root of 3.
That's because you see that 920 lambda 8 is square root of C11. So automatically, because it's 1 over 3 times square root of 3, right? So it becomes 1 over square root of 3. So that's very... so the square root of 3 is the one. Yeah, it's a multiplication of the... so
well, this
lambda
is the
8. Lambda is square root of 3 times lambda of 3. Lambda 8 is square root of 3 times lambda of 3. And that's you know, if we compare, if we do that, and that's why you get 1 over square root of 3. You know.
I don't follow you, because this is the inverse of that, isn't it?
No. The way it works is lambda 8 will be lambda 3. I don't know why they didn't put that. Lambda 3. It's minus. Okay.
Yeah, it's minus.
So, yeah. So C11 plus C22, right?
Yeah.
C11 plus C22 is 1 over 3 times that matrix. Okay. Because 1 over n, whatever SUN, because the n in this case is 3, right? It's SU3, right? We are talking about SU3.
No. It looks like if we go C11 plus C22 times the square root of 3 equals 1 over 3.
Yeah, that's because
times this matrix.
See, it's a SU3 generator, right? So you go back up. It says that for that to calculate, it's 1 over n times that thing, right? All the way up.
Oh, no. That's, yeah, I see what you're saying, but n here, would be SU3, but
So
wait, SU3 is not the square root of 3, though. But that's what I'm trying to say, that if you look into the SU3 matrices, they are linear combinations. So that's how it works. So this would be like a gluon, and this is a different gluon. And the way that they normalize it for the linear combinations is to have terms like this, where they multiply it by 1 over the square root of 3. So I think you really just need to know how SU3 is constructed in order to understand what these terms are. So that will be my interpretation of that. So I think we'll move on. So similarly, the diagonal generator of the isospin group SU2 is constructed from the diagonal generators. Right. So anything that's in here, and probably good to remember these letters, but we'll move on. Finally, the generator here we have the U1 generator, must be diagonal and of the form of a unit matrix with respect to SU3 as well as SU2. Furthermore, it is required to be traceless. Okay, that's interesting. The only way to achieve that, this is the following combination up to a factor. So here we have this again. And where we employed the matrix defined by 9.6, the complete set of SU5 generators 1 to 24 will be determined in exercise 9.1. So here are the exercises. Now, we have the problems, we have the solutions already given to us. I'm not a big fan of exercises.
Yeah, I'm not. I think examples are better than exercises, you know?
Yeah. So
work out examples.
Maybe I'm sure this will be very useful from the point of view of understanding, but I think we will just move on, because I think we got this. We know all about this. Although there is some interesting points being made here to describe the transitions between multiplets that belong to different subgroups, that is between the subgroups of these subgroups. such transitions are mediated by the gauge bosons X and Y. So here are X and Y and or whatever. So because these are the mediators between these two subgroups, right? We spoke about that before.
So they are just attaching one matrix to the other. They are kind of gluing together two matrices. I think.
Well, this is SU3 up here. Remember? This is SU2, and then U1 goes straight through the center of those. So that if we remove these groups here, then we are just left with these. Like we forget about this. We're just left with these, and these such so these subgroups here are mediated by these groups, right? Because they're mediating the other two groups. You know what I mean? Through cross products or whatever, or cross terms and indices. And so we'll see later on in section 9.3 that these are the X bosons and these are the Y bosons. And they just use X and Y because they don't know what they are. They've never seen them before and they don't exist in nature. The remaining SU5 generators are these. Okay, and finally, the U1 generator.
So they're not really zero. They're just missing there. There's nothing in there. There's no zero. They're not zeros.
They just don't bother writing it in, I think.
Yeah.
They are all zeros, yeah, probably. Yeah. Okay, so here we have we have this U1 matrix, traceless matrix times 1 over square root of 15. Now, could the 15 be, it should be 1 over n or whatever, but when we talk about the dimensions of the irreducible groups, subgroups, we've got 5, 15, 10, 5, 24. So sometimes it's over 5, sometimes it seems to be over 10. But I don't think that is the solution to this problem because we never see 1 over 24 or 1 over, and then it's why would it be the square root? So
I'll show you I think on another screen. Let me show that simple calculation, which I think is the one. But we have to go back up. Let me pull up a paper. This is what I think it is.
Okay, so we can't see what you're doing, Rajan.
Yeah, I will put it in once I write it. So C something is 1 over n something. Let me just write down and then I will show you. Then if we have S23, then we have C, whatever it is 1 over 3 times. Then you multiply by root of 5 over.
You could use
square root of 3 of 5. Yeah.
Okay. You could use the camera on your phone to show us what you're doing, maybe. Oh, wait a second. I can have that.
Yeah, I just had to put that on.
No,
can you see it now? Yeah, I was trying to do it afterwards, but you already put it.
Yeah, so it's already up. So I can make that bigger, or can I? Oh, it's not working now for some reason.
Can you see it?
Yeah. Kind of. For some reason. Oh, yeah, we can see it now. Yeah, kind of.
I just arranging so that it's straight, straightened out. I want to straighten it out.
Yeah, there's 1 over n. I think I can see. It's kind of a bit blurry for some reason. Oh, yeah. 1 over 3. Yeah.
Okay. Blurry.
It is very blurry, yeah. Well, I'll just go back to that. And you keep working on this.
How about now? Is it clear? I had to just.
Oh yeah.
The pen is. I have to write again.
Going over things though.
The ink is not very. Can you see it better now?
A little bit, yeah. One over 3. Yeah. Okay, so what point are you making, Rajan?
Okay, what I'm saying is that so the idea is that you know, this is a simple thing that earlier they have, right? This is what the basis is. 1
Yes.
over 1 over n. So if you have SU3, right, the C, whatever the C is, becomes the n equal to 3, right? N equal to 3 for SU3, right?
Yeah, and well, yeah, I guess you're right. Yeah.
So this is the n, SUN. So the n is 3, right?
I guess.
So 1 over n becomes 1 over 3, right?
Fair enough.
Okay. Then we are multiplying this C by 5 over 3. That's, I'm not sure why.
Square root of 5 over 3.
Is it square root of 5 over 3 or let me see. We have to go back to your thing.
Well, I'll just take a quick look because let's see. Well, you know, the square root of 5 over 3 appears a lot.
Yeah. So let's say this is the one, right? Let's say
well,
this is the one.
Sometimes they're multiplying like U1 matrices like the
I think
diagonal
it's 3 or 5, I think. 3 or 5.
Well, it's 5 over 3. The square root of 5 over 3. I'm looking at it. Like, so I can tell you what it is.
Oh, this one?
Yeah, the square root of 5 over 3. Yeah, it's always 5 over 3, Rajan.
So let's say it's square root of 5 over 3.
There was also 1 over 5, which we said was the SU5 group. But
yeah,
see, the thing is that the SU3 is a subgroup of SU5. So we're never dealing with SU3 on its own. So the n is never 3, I don't think.
Oh, okay. But you can see that what happens here.
Also, Rajan, I just explained to you what 1 over the square root of 3 is. It comes from the SU3 subgroup. Like if I show you the Gelman equations, I'll just look them up here.
But the earlier ones you can explain based on this simple calculation. When you multiply it.
Are you doing? Yeah, I'm interested, but I mean I don't agree with you. But if you have something, then I'm interested.
Yeah, if you can pull up the earlier ones, can you pull up the earlier one?
Well, wait, yeah, I can do that. I can go back to this.
Yeah.
Well,
go back to the earlier one.
Prove my point straight away here. If I just share screen, will this sort out the?
Then we will come back again. Yeah.
It will override the thing. Good. All right. Right. That is that. See here, Rajan. These are the Gelman matrices. So lambda 1, 2, up to 8, and for the eighth one, it's a linear combination times 1 over the square root of 3. So that's where that comes from. Okay, so that's it. So we'll just move on from that.
Okay.
Okay, but when I hit hide, it goes back to there. Right. Okay. So you see there one. Well, that's 1/3.
Yes.
But anyway, we know that it's this 1 over the square root of 3. That's from SU3. Okay, let's continue on. We've got all this. We've got our X, Y bosons and more of our SU2 and U1s. We already looked at all of this, did we? But I don't remember this. Altogether, the generators lambda 1 to lambda 8 form the, right, we know that. Well, the generators T13, yeah, we know that. Or tau, the operators lambda I commute together with all 3 operators. Right, tau I, implying the subgroups SU3 and SU2 commute with each other. Of course, this is also true of the subgroup U1 generated by Y, since Y is diagonal with respect to the subgroups. the lambda 1 to 8 describe SU3, lambda 21 to 23 SU2, and lambda 24 SU1, or sorry, U1. Altogether, these 12 generators represent the new subgroup. This group is a subgroup of the complete SU5, which is formed by all 24 generators. So that's interesting. So the first 8, then there's 3, 4, right, so that's 12. And then there's another 12 in the full group. Right, so that's basic. We don't need to talk about that, which means that the direct product group is embedded. Yeah, we got that. Formally speaking, the embedding of a group A into implies that the Lie algebra of the generators of A is a sub-algebra. Yeah, that's also very basic. From the discussions of this model, we recall the hypercharge of the lepton doublet, which is made from the electron neutrino and the, what is that? The positron, not the positron, the
electron itself.
Yes, thank you. Is -1. Okay, this is convenient to normalize the corresponding operator of the hypercharge appropriately. So this is a normalization factor then, square root of 5/3.
Yeah, that seems to be.
It is important to note that the left-handed doublet, lepton doublet, belongs to the complex conjugate representation of the subgroup, which is our Young's diagrams, in terms of which the operator for the hypercharge is given by minus this hypercharge group. In order to see this, we consider the group operators rather than the generators. Okay, so the group operators are going to, so the action on the matrices, so there's your matrix and it's I times A, whatever that is.
Alpha. Yeah.
Alpha, right. But it's not the fine structure constant, it's something else. Only in this way that is with respect.
Is it the angle? Is it the angle?
Yeah, that's what I was gonna say, but that would be theta, wouldn't it?
Some kind of an angle they were talking earlier. What was that angle? Very important angle they were talking about. Weinberg angle. Something like that. Is it Weinberg angle or something like that?
No, probably not. But they do mention it up here, I think. Oh no, sorry, the X. It's
alpha.
Here.
Where is the alpha?
Yeah, I'm looking for it. Yeah.
Yeah, there. Alpha.
No, these are indices.
Yeah, they're different. They're different alpha. That's not the alpha.
Okay,
they're mixing symbols that they need explanation.
Well, we know when it's a sub thing that it's an indices.
It's different, yeah. It's different.
So you can kind of work it out from the context. Okay, so we'll just continue on.
Yeah.
It's not. We don't need to get too bogged down, maybe. But
yeah,
I suppose if we skip over things, we might lose something of importance. So
that's the whole.
It's hard to know. Taking into account the isospin operator, we find the operator of the electric charge in terms of the fundamental representation 5. What fundamental representation 5? Okay, so this is some sort of T hat 3 plus half of the. Oh, this is the third isospin component, is it, or something? And then that's it could be. And okay, so we get this anyway. According to 9.24, charge operator for the representation. So that's what they meant by representation 5, and then there's this other one. It's given by minus Q hat. Okay, because it's charge. The form of 9.25 exhibits the consistent unification of the elementary fermions within the quintuplet of the SU5. So that's fine. Well, SU5 would be a quintuplet, wouldn't it? Because there's 5 of them. As will be shown in example 9.2, we must assign the last 2 components of the lepton anti-doublet. So when it has a C up here, it's anti. And notice that the chirality also changes with the anti-particle, which is interesting. whereas the first three components representing the color charge group SG3 corresponds to the particles of charge minus 1/3, which we know about already. They have partial or fractional charges. The latter can only be color triplet and isospin singlet of the right-handed D quarks. See table 6.2. Thus, the 5-dimensional representation is given by this.
What is a D quark?
A down quark.
Down.
Let's look up table 6.2 because that sounds important. Where would we even go about finding such a table? 6.2, is that in chapter 6?
Could be, yeah. Quite possible.
Chapter 6. 6.2. Ah, yeah, because look, these are all about quarks.
Yeah, there's these. Oh, they're down. For you.
The next table.
Yeah.
We need the next one. 6.2. It should be in here. 6.2.
Yeah.
Values for the weak isospin and the weak hypercharge of the SU2L cross U1 hypercharge theory. According to the Gell-Mann-Nishijima formula, Q equals the, this is the third isospin times the hypercharge gives the charge. Third component. So the physical charges of the particles can be calculated. Usually left and right-handed particles, example, are those. Leptons and quarks differ in their weak isocharge. I'm getting this name wrong. It's the weak isocharge or something like that. The third component.
Right?
Sorry, what?
Is it weak isospin? No.
That's it. Thank you. Yeah. Quarks. So we have doublets, and that gives you those. Singlets, and that's this. I'm not sure what these values in the end here are. Leptons. Oh, this is the hypercharge. They should have had these should be up here as well. Right. These are the hypercharges. Is it the hypercharge when we sum them all together, or is it just the hypercharge?
So 4/3. Are they connected for 2/3?
I don't know. Like maybe it's when you sum them all together in a row, or I don't know. Well, actually, if this is a third, this is a third, and this is a third, then you get. Well, no, then you just get one.
Yeah, they're not traceless, I guess. Something like that.
I don't know. Well, it's to do with this whole how is the hypercharge actually calculated? I still haven't figured that out yet, and neither have I figured out how the weak isospin is calculated. It's easy to calculate the charge based on those, but without knowing how these are calculated, I'm not sure. Okay, and then for doublets, I mean, I think it's a bit strange that the hypercharge is 1 or 2. It's no, maybe it's not actually. That's kind of normal. Okay, predictably, I knew about halfway through reading that would turn out to be kind of useless.
Some of them are calculated from Feynman diagram. Some of the things.
How do you know that?
Is it calculated based on? Some of them are based on the Feynman diagram.
Doesn't seem to say that. It says according to the Gell-Mann
formula.
Physical charges. Okay, usually. So the thing that why did we come over here? It's something to do with the D quark, yeah, down quark.
Yeah.
Down quark. Where the heck are we? That'd be a good name for a dog, yeah. Quark. Dan Quark.
D quark.
Dan Quark. Dan. Oh yeah. Okay.
They're not dark.
This is it. The latter can be only the color triplet. Okay, the isospin singlet. See, this is getting very technical, I think.
Yeah.
But there we go. We get this kind of vector, which is a 5-dimensional representation, and then
so it's U5 spinord. Spinord. They're finding out the spinors.
We have the first three. The first three are quarks, and the bottom two are part of the SU2. So this is SU3 and then SU2, and P equals 1 to 5. So this symbol here, the psi sub P. So this is psi 1, 2, 3, 4, 5, right? Okay, and there's the subgroup, five-dimensional representation subgroup, which was mentioned up here. Taking into account the isospin operator. Right, hang on a second. Only in this way, in order to see, we consider the group operators rather than the generators. So that's why we're getting into this group operators rather than the generator. Only in this way, that is with respect to the 5-hat representation is the hypercharge of the form. So this is 2/3, 2/3, 2/3. So this would be, since we're only dealing with the first generation of quarks, they have charge 2/3. So this has to be down, down, down. And then these are leptons. But the appropriate value is -1 for this doublet. So this is a doublet. Taking into account the isospin operator, which is oh, hang on, what's the isospin operator? Oh, this is leading us up the garden path here. Was this the isospin operator or something? 91. I don't know. I forgot the number as I scrolled up. That's fantastic. Yeah, well,
there are two different matrices. They were saying the weak isospin one type of matrix, and the hypercharge is another type of matrix. So they're combining the two.
Yeah, so it looks like it's this anyway, Rajan. Look, it's
okay.
Similarly, the diagonal of the isospin group. So it's just a generator for the isospin group of SU2. To be honest with you, I'm not entirely sure. Isospin group of the SU2. I'm not sure what that means. I know
SU2 means the first three are 0, because SU3 comes there. The SU2, the diagonal first three are 0 for SU2.
Yeah, we know that though, but it's more just technically, what does isospin refer to? When you have isospin of like a proton or a neutron, you can treat it as if it's got spin up or spin down, but it's kind of a thing called isospin.
Yeah.
So maybe it's something to do with that, and then you can like we say, we don't know how to calculate the hypercharges or the isospin.
Is it the rotation? Like isospin is if you rotate in one direction versus the other direction, it's the same?
I can't remember. No, it's to do with how many. It's to do with like this. If we think of the spin of a particle, it can be either up or down or something, and then you can treat like neutrons and protons as if they have a spin based on like their components, I think.
Yeah. The spin, of course, has to do with the magnetic vector, right? The magneton on the magnetic vector.
Right, but it's something really simple. You know, the way you have all of these things like the lepto number and all of that, where you just, it's kind of like that. It's something very basic. Like it comes out as like the proton has isospin 1, I think, and the neutron has isospin -1. It's something quite. It's quite a basic but a pretty clever insight. And actually, it seems like most of quantum mechanics comes out of this concept, which is weird. Okay, but obviously. So the index, we've got this. So this is an SU5 spinner now. Okay, because these are all spinners. Note that the antiparticles corresponding to the SU2 doublet are represented by the doublet. Okay, the sign of the helicity is reversed for the antiparticles. Sign of the helicity. Well, this is essentially the result of 9.2, which is the next of example 9.2, which is, except for the minus sign in the case of the antineutrino, quite plausible.
It's something to do with the precession, right? Is it something to do with the precession because of the magnetic thing?
Helicity. The helicity.
Yeah. Is it connected with the precession?
Helicity is the projection of the chirality onto the direction of motion. So if it's moving in the x-axis, you project the spin, whether it's up or down, onto that axis. If it's, you know, that, and that's the helicity. That's as much as I know. That's my definition of helicity. Okay, so I don't even really use it. So it's a good question. I mean, why are they talking about it? And where does it even say sign of the helicity? I would say maybe they're talking about this. The chirality would be the sign of the helicity. For fields of antiparticles with spin 1/2 are obtained by the charge.
No, they don't mean that the chirality, because particle, if it's right-handed, the antiparticle need not be left-handed, right?
No, apparently they're saying yes, it does. Because look,
really?
They have this this doublet that's left-handed, and these are normal particles. But then when we go down here, the anti-doublet has these antiparticles in it, and it's right-handed. So they're always switching the chirality as well as the charge for matter and antimatter. It's interesting, which makes total sense, really, when you think about it, because of when you spin one, the other one's going to be conjugate or whatever. So it's going to be the opposite. Okay, and you see it here. Oh, no. Okay, let's just continue on then to find... All right, where the operator of the charge conjugation is fulfilled to fulfill this. Now, I'm sort of spacing out here on these equations. This constraint is satisfied by choosing, for example, or these look like those gamma matrices, don't they?
Are they?
Well, what else could this be? The gamma. We haven't seen that before. That's gamma matrix 0. Yeah. So this is the particle. This is the gamma matrix 0. This is the, what is this? The adjoint. Yeah. Upper 4 vector or something. Okay. No, this is the
conjugation of the whatever that.
And then function. This. Yeah. This is the. Is this a? It's a 4 vector anyway, but it's got some funky Hermitian value or something like that. Okay, I've forgotten what the star means. Charge conjugation.
Charge, yeah, conjugate. I mean, the conjugate of the first one.
Right. Okay.
Complex. It's actually complex conjugate, I think, when you put star.
Yes, but is this are these complex values? I suppose it could be.
Yeah, let psi star equal to 1, something like that.
Okay. And similarly for the antiparticles. Are we skipping over this too brazenly? In order to find the behavior of chirality eigenstates under charge conjugation, we consider
so when you say the left-handed thing, the C needs to be conjugation, right?
Oh, sorry. Maybe you don't want to answer that question. I'm just saying I think these are Clifford algebras or something of the sort. And that these are the gamma matrices.
So the chirality changing here. The left-handed thing with the charge conjugation changes to right-handed of the conjugated one.
Right. Okay, that makes sense. Thus, the charge conjugate state of the right-handed electron is a left-handed. Yes, so this is what we were saying. Applying the operator of charge conjugation to isospin doublets, situation becomes more complex. So we've already learned from the example of hypercharge, charge conjugation versus the sign of the eigenvalues of generators that generate symmetry transformations. This is due to the operation of complex conjugation, which is part of charge conjugation. Hence, by naively applying charge conjugation to the particular components of a lepton doublet, such as this, resulting doublet. Right, okay, so it changes it from L to OR.
So charge conjugation does change the chirality.
Yes, yeah, because we can see that this is the antiparticle of that, and that's the antiparticle of this. Would have isospin third component 1/2 and plus, because they're opposite as well. So that's interesting. The third component isospin for matter and antimatter are different by sign, it appears. Because I think I read somewhere else that they were just identical. So that's going to change all of. Remember, I was working on the I Ching leptogenesis particles.
Yeah, yeah.
And I had them both the same because I read somewhere that they were the same. But this seems to say that
you have to correct for that. Huh?
I'll have to go back and correct that, because that was a big stumbling block when I realized that. I read, oh, that meant that there were particles that had a hypercharge of 5, and then so that kind of put a spanner in the works. But I just like ignored it, and like, you know, I just said, well, it just applies to matter particles, then left out the antimatter. But if this is the case, then then there is no hypercharge of 5 for any of the particles, whether matter or antimatter, which is good. So I'll have to rewrite that paper though, but otherwise it's all good. I think you know, it's good when you reformulate something because you're not sure, but you want to go with the best guess you have, just to reformulate it in a sort of a weak way so that you don't have to correct things too heavily when you ultimately discover you were wrong. For the upper and lower components, respectively. Oh, wait a second. Of course, this cannot be right, however. The following simple prescription will yield the correct results. We only need to rotate L around one axis or two axis of the isospin by 180 degrees. It's common to choose the 2 axis to perform the rotation. I'm worried about that. Naively applying the charge count, which resulting doublet. Oh, right. So it says, of course, this cannot be right. So maybe these should be the same. What do you think? Yeah. So ignore what I said there about leptogenesis and isospin.
Oh, so it should be same.
Yeah, I think they're saying that this is not correct. So that's good news. I don't have to rewrite that paper. It's common, right? So there's some rotation in isospin space that gives the third component of the isospin. So they're obviously not pseudoscalar because it's not changing the sign. And then axis 1 or 2 would be either the z-axis or the y, the x-axis or something. So here's your rotation of your groups, and blah blah blah. So it gives a minus where we have used the relation. Okay, just the correct charge conjugation isospin doublet. It's given by the additional rotation in isospin spaces, that is. Oh, it comes out like this, is it? Which is different to this. Yeah, it's just upside down. So it doesn't seem like they were arguing against this. Maybe they were arguing against this, and I don't know about this. Oh, right. Maybe they used this to say, well, that can't be right. Our answer can't be right because we're getting the wrong answer here. So then they redid it, and they get this, which presumably has the same isospins. And so they were happy with that. From our previous considerations, we might be... Yeah, okay, we did that. From our previous considerations, we might be tempted to combine, isn't it? The left-handed charge conjugation particles in a quintuplet. However, this is not possible since the left-handed d quarks belong to an isospin doublet. Do they? Wouldn't the quarks be in the SU2? Oh, yeah, okay. Okay, so we can't do that. So these are kind of doublets here. Left-handed. Charge conjugated particles. However, since the left-handed d quarks belong to an isospin doublet. Oh, okay. 629. So these are the doublets using. Oh, wait a second. It's 629, didn't it? Ah, no, yeah, it did. So we need to go back into the other. We're not going to do that then. Whereas the left-handed positron as the conjugated particle to the right-handed electron is represented by an isospin singlet. All right. Okay. So one is singlet, one is a doublet. So you can't put them into these quintuplet things. And the best we can do is to form a SU5 anti-quintuplet that contains the conjugated left-hand particles corresponding to 9 to 6, corresponding to this. Okay. What did it say? So yeah, so it was corresponding to that. One. And right, so they just turned it all into anti things. So does that mean it's now left-handed instead of right-handed? Yes, it does. Okay. Blah blah. Note, however, this is not an independent assignment. The superscript denotes the antiparticles. The antiparticles quarks are left-handed. Both are SU2 singlets. Frequently, antiparticles are right. Okay. In order to prevent this, all right, we have up to now given SU5 assignments to the right-handed d quarks and to the right-handed positron, the electron neutrino, as well as to the left-handed d quarks. Okay, so they're just saying what they've managed to assign. Question remains open. Which SU5 assignments will be given to the left-handed fermions? Okay, so they haven't done these ones. Is that what they're saying? The doublets or something? Because like
C9.27a.
Well, because they've done D or DB, DG, L, right? Because oh no, they did the right-handed ones. Sorry, they did the anti-left-handed ones. So they haven't done these. So, well, that's weird actually, because aren't they only interested in the left-handed ones? Didn't they say that? SU. Oh no, it's just.
Didn't they say that left-handed ones exist, the other one doesn't exist, something like that?
Well, that's maybe true, but the point is they did say SU3C. So these are, which covers the quarks. So it just get a bit confusing actually. So maybe you can have right and left-handed quarks, but only left-handed SU2, electron neutrinos and electrons. So they've done the left-handed electron and so they're only the left-handed ones of these because they're SU2. But they haven't done the left-handed quarks, is what they mean there, really. And the singlets, the anti-left-handed ones of these, they haven't done. Which is weird, because why would they want to do... Because the weak force wouldn't bind to the... Either it doesn't bind to the left-handed matter leptons, or it doesn't bind to the left-handed antimatter ones, one or the other. So I don't know why they want to include those. Because it wouldn't bind to one or the other. And presumably the reason why they're looking at the left-handed ones is because of the symmetry breaking and the fact that they don't bind to that.
Is it because non-commutativeness?
I have no idea. To achieve this, i.e. to determine the classification of the elementary left-handed fermions, that is 927A. Where did that go? 927A? Oh, these guys. So we were just, oh yeah, we're here. To the singlets, right? As the question remains open with which SU5 assignment has to be given to the left-handed fermions. Sure, they didn't need to do that because you can see them there. To the single, or maybe it's different. The singlets. To achieve this, right? So they're just looking for different matrices that need to combine. So these are the ones they haven't done yet. They just want to assign matrices to this. Achieve this to determine the classification of the elementary left-handed fermions, as well as the singlets, into further SU5 multiplets. We need some additional tools from group theory. Excuse me. The problem is, how do we decompose the irreducible representations of SU5 in terms of tensor products of representations of the groups SU3 and SU2? We start from the trivial decomposition of the fundamental representations of SU5. So here's some decompositions of the fundamental representations. Now, it's interesting that you can decompose a fundamental representation because surely a fundamental representation is fundamental. But you're going to do it anyway. Decompose. So 5, which is just 5 ones, goes, or 1 5, whatever, goes to 3 and 1 2 plus 1 3 and 2 of those. So 2 plus 3 equals 5. And then whatever these guys are.
3 plus 2 is 5. And then
whatever they are. I don't know. So 3 and 1 and 1 and 2, they're saying that this is some sort of trivial decomposition where we have alternatively employed the notation of Young's diagrams and the notation in terms of dimensional representations. The indices 2 and 3 indicate whether the representation oh, right. Yeah, that was another way of looking at it.
Yeah, so 3 is a SU3, 2 is SU2.
Yes, using the distributive property, we obtain the direct product of the two fundamental representations. So here's the distributive or the direct product of these two, and they're going to decompose them and then take the product of the decompositions, which will be 3 by 3 times 1 plus 3 times 2 plus 3 times 2 plus 2 times 2. So it's basically just a quadratic equation of sorts, which results 3 by 3. These stick together. And then that forms this as well. So the direct product gives you this one and this one. Two of these, because we just add them together, plus the direct product, which is the opposite, which is just the same thing. So that's wait a second. 2 of these is those. 1/3. Well, I'm not entirely sure.
Oh, the Young diagram. They're using the Young's diagram, right?
Yeah. Oh, yes. So 3 by 2 will give 6, right?
Yeah.
2 by 1, or 2 by 2 gives 4, but because they're all in a line, the dimension is 1. You're not gonna get the 6. So that's
you have to go back to the earlier representation and then use that and then.
Oh, wait a second. Sorry, just I thought the 3 here is for SU3, isn't it? So it's not 3 by 2. It's 2.
It's only one, right? It's only one row. So
yeah,
one row, 3 things. And the other one is column 2, and then 2 of that, something like that.
Well,
so again, it's 1, right? Because
I think they said the indices 2 and 3 indicate belongs to SU3 or SU2.
Yeah.
So they're saying this is SU3, 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 SU2, SU2, SU2. So they're trying to. So basically, they're basically going through some sort of complicated thing to find the subgroups. Let's just assume that they know what they're doing and they get the right answer. I think that's fair. So we don't need to care about that. We're just going to move on. Quintuplet of SU5. Because if they'd made a mistake, someone would have pointed it out.
Yeah, we don't go into minute calculations, although we can, but it will take a long time.
Yeah. And I think we kind of get the general idea there. I mean, we could return to some of this at a later stage as well.
Actually, you can program this and then let the computer do the calculation. And we should be able to get the answers.
Well, for sure, we should look up some code to do with this in future.
Yeah. Because computer, is a calculator, so we don't have to.
Why it has to all be written out by hand doesn't make a lot of sense.
Up to certain calculations, it's okay, and calculation will help. But after that, we use the computer to calculate.
We decouplet, anti-decouplets, SU5. So here we're into the gauge theory side of things. We're kind of back to this 5 times 5. We have the direct product. Gives us the same results. Decomposition.
They are going back and forth with Young's diagram and the algebra. So it's like a geometry.
Since the gauge bosons of the color group SU3, gluons as well as the intermediate bosons and photons are contained. Make the following assignments. There is SU3 octet of gluons, 8-1. Right, so they're just assigning the particles to the different subgroups here. I think. Where did they get 8-1 from? Oh, they did. They got 8-1 somehow from this. So we'll just believe them because they know what they're doing on this. And that's fine. They got their gluons, the bosons, and the hypercharged bosons. In addition, there are 12 more gauge bosons belonging to these representations. These form the isospin doublets of the bosons and their antiparticles, which are colored. Common to use the following notation. So it looks like these are the 12 weird bosons that are X and Y's. As we will prove in the next exercise, the corresponding gauge charges are Qx plus 4/3. Right, so they found the charges of these particles, 4/3 and 1/3, which is the same as the some of the quarks. Interesting. And also the same as the I Ching particles, the what are they called? Hexa-Wen particles and stuff. Right. Yeah. Evaluate the electric charges of the. Oh no, these are more.
So these are unknowns. X and Y are unknowns.
They've never. Yeah, they don't exist. They've never been found. I mean, I should say, not that they don't exist, but
they're just imaginary things.
Yeah. I suppose they're trying to fit all the particles into the new into their generators. And what they found is they found
before generators.
Yeah, and what they found is that there's some areas that aren't filled up. So, okay, that's fine. I mean, that's a bit like what happened.
Oh, this is how they fill up the standard model?
Yes. Table? So it's very similar to when I was putting in the particles into the 24 cell, and I found that there was 8 vertices that weren't filled. So that meant that there was 8 new particles that hadn't been.
Yeah, I also found when I did that, why I had to get 8 by 8. I kind of figured out that different way particles. Because you have to have mass, charge, all those things, parameters.
Okay, so here we get into the.
Christian was pointing out.
Mass charge. Oh yeah, I remember. Or I remember part of that. So let's So this is what are we talking about here? Where we get into the Higgs mechanism and all of that. Describe the Z boson.
The W is the W boson, right? W and Z.
Yes. And then we have the Weinberg angle, charge conjugation. So they just stick in the stuff for the standard model here. So all of this must be to do with SU2.
SU3. The top one is SU3, right?
Sorry, that's what I meant to say. Thanks. Yeah, SU3. Where A hat mu is equal to, so A hat nu.
That's a field, right? Oh, no.
Oh, that's
Oh,
time.
that's the field, yeah. Gauge
Oh, so
field.
yeah, this is the name of that, right? Yeah.
The gauge
So-
field.
Right. Yeah. This is the gauge field.
Yeah.
Yeah, for the photon, the electromagnetic gauge field.
That's for the photon?
Well, it is the gauge field of electromagnetism, isn't it?
Oh.
A sub U.
Yeah.
Yeah, because it modifies the spinors in this case would be for the SU, the quarks, modifies those so that they have conservation of charge, and not charge, but mass and energy.
So
and
it's
all that.
kind of supposed to be the complete math of that.
Yes. So you see, they just do this gauge transformations using kind of algebra, whereas for ages now I've been using the gauge in terms of like rotations with matrices, but that's not. I don't think that's really correct. I mean, you could look at it that way in one sense from like a Lagrangian point of view. That's not how they do it. They do it all in terms of algebra. So it's interesting, but I don't think it's a total defeater to the work I'm doing or anything. So with these ingredients, we are now in a position to take a prediction for the Weinberg angle. In the framework of the unbroken SU5, the essential point is that the gauge covariant derivative of SU5 is this. Okay, contains only a single coupling constant G5. This is easily understood by the analogy. Example 4.8. Find the coupling bosons are given by this. Okay, so this is the coupling constant that we're just adding to. Whereas the B bosons couples to the hypercharge according to this. There's a hypercharge, there's your B bosons, and then the coupling constant and some other coupling factor that we still haven't figured out. Understanding this relation, let us consider these are the, you know what they are, and these are the Pauli matrices, and then this forms this, and we take that out to there, and we get that, and the results.
They're just sticking together different things, I think.
Yeah. The coupling of the fermion fields is defined according to via minimal coupling, namely. So these are the coupling. Last term represents the interaction. This last term. That makes coupling. There's your electromagnetic field, gauge field. Okay, in correspondence, it contains the coupling of the U and B bosons. W sector, B sector coupling. So that's this. Yes?
Oh,
no, wait.
Is how they consider W and W minus, W plus, Z plus C minus, something like that.
W plus what? Sorry?
Are they deriving how they get that W plus W minus and then Z plus C minus? That type of thing. That's a weak theory, right? Okay.
W plus minus. Oh, do you mean the weaks? The weak bosons and the Z bosons and all that?
Yeah.
It's kind of, yeah, it's in that general area. It's moving towards that with the Higgs mechanism and all. So if you see coupling constant times the adjoint psi 4 vector times gamma times the gauge. And then, so we have this, the thing. The gauge goes away. What's left? That's gone in there. And that. Don't know where the gauge disappears to and all of that, but maybe it's already.
Oh, it's in the G. G absorbs that gauge there.
Oh
the
yeah.
G5 and G5, but it absorbs that.
The gauge kind of disappears anyway, doesn't it? Sort of kills
No,
itself.
the G5 has that gauge field.
Okay, you'll have to show me that sometime. I haven't come across that, but I don't. G5 is
What is G5?
is the coupling thing, right?
Yeah. But the gauge field comes in the coupling. Either the gauge field comes in the coupling.
Yeah, possibly. Okay, that's something that I'll have to look into.
Yeah.
Well, I mean, the coupling and they're very connected, aren't they? So those equations are obtained for the SU2 U1 theory with the corresponding gauge covariant derivative of that. Okay. Thus, we identify the coupling constant G, or G prime, of the Glashow-Solem-Weinberg theory. So there we go. Maybe this is where it came from all along. 3,5 coupling constant. Consequently, the prediction of the Weinberg angle within the SU5 symmetric gauge theory is 0.375. Obviously, the value deviates from the experimental result of 0.23. In order to understand the considerable disagreement, note that we have obtained the Weinberg angle under the assumption of an unbroken SU5 gauge theory. This cannot be the case since we already know that SU2 U1 symmetry of the theory is spontaneously broken by the Higgs field. To date, moreover, there are no experimental indications of the influence of the additional gauge fields X and Y. Sparks leads to the hypothesis that these fields must have significantly larger masses than the W bosons. That is to say, the SU5 symmetry is assumed to be realized only at very high energies. These happen to be about 10 to the 15 GeV in order not to conflict with the well-known lifetime of the proton. In other words, below the energy threshold of 10 to the 15 GeV, SU5 is a broken symmetry. Only for larger symmetries is it intact. However, in quantum field theory, the coupling constant G depends on the considered energy, or more specifically on the momentum transfer. As we shall discuss below, and this for energies lower than the mass of X, Y bosons, the energy dependence of the coupling is different for the particular subgroups SU3, SU2, U1, which consequently yields an energy-dependent Weinberg angle. Therefore, it's quite possible, indeed, we shall confirm that it is in that 0.23 for the lower energy region, experimentally accessible to date, whereas for the large energies can reach value of 3 divided by 8, which is 3 divided by 8 is this value. Since the symmetry breaking can be neglected, from this requirement, a prediction of the mass of the X and Y bosons can be attained, must be compared within the bound for the proton lifetime measurements. In order to understand why X and Y bosons in principle can lead to the decay of the proton, let's consider, for example, gauge field XOR equals X1 according to couples to the X 5 times 5 matrix. Does that make sense, right? Because that's where X1 was. Applying the matrix to the elementary quintuplet of SU5, we obtain, here we go. So these are elementary quintuplets and then coupling constants and gauges. And then we stick the boson in here for some reason instead of the gauge, I think. And then we have the adjoint, blah, blah, blah. It gets a bit muddy here. And then, pops out with this. So this is the D quark couples now directly to the positron. So D and the positron, that is the D quark, is transformed into a positron. To understand that the X field can transform a D quark into a positron in diametric. So basically the X field transforms D quark into a positron, which is a problem because positrons or leptons and quarks aren't meant to transform into one another. And if they did, it would mean that the proton could decay, couldn't it? Because one of the D quarks in the nucleon could turn into a positron, and therefore the nucleon would disintegrate, ending the life of the proton. So that's it. So, this is how it's done matrix-wise. Now, I'm not entirely sure how they get this. But
They just stuck together SU2, SU3, SU2, and SU1, right? Stuck together, all these two matrices together.
I guess. Oh, well, this. Well, it looks like XOR, which was X1, right? XOR was X1, which was this. And it seems like they've picked everything except X1 to do this, right? It should be this. But they picked all the other ones. And then they have this, which is just what they have. That's one of the generators, presumably. And then then the interaction is this times this, which gives 0 times this, which is 0. This times this, which is this, and so on and so forth. 0 times that is 0, so it doesn't appear. And then we get U. So they put in the space-time index, and then I think that's it. So apparently there is one other thing that these X and Y bosons are called leptoquarks. Okay, so I think we covered a lot of that. All these processes have in common that the baryon and lepton numbers of the initial and final states differ by the amount -1, the lepton number of the particles. Positron and anti-neutrino electron is -1 by convention. The SU5 theory thus conserves the difference B minus L. In other words, B minus L represents a conserved quantum number. The X and Y baryons carry the quantum number B minus L 2/3. Processes such as the transformation of a neutron into an anti-neutron, so-called oscillations by analogy with the oscillations between the states kaon, anti-kaon due to the weak interaction. So it cannot therefore be described within the framework of SU5 theory if the existence of such transitions was experimentally observed. The SU5 theory must be rejected in principle. Okay, so I think we kind of covered everything there. We don't need to go too much further into that. And is there anything else?
Covariant derivative.
Oh yeah, covariant derivatives. That's interesting. Because then what's the other one? Covariant and
gauge transformation. The wave function.
Contravariant, isn't it?
Contravariant, yes.
Something like that. Okay, 4 gradient to the primed wave function. Well, that's all very interesting. I don't know. U hat. Expression. Well, where is? Oh, this is it here, isn't it? The partial differential of U and all of that. Covariant derivative, which is really just the 4 vector, but it's kind of everything's partial derivatives of the 4 vector, of the contravariant one. I think that's what it is. Anyway, I suppose you don't really need, you just need to know what the equation is, and that's enough. So I think that's basically how most of these people operate. They just know what it is. They might not know anything deeper than that. Certainly that's how the mathematicians work on this. What are we looking at here? Is this just exercises or example? Oh, this is right. Constructing.
Are they constructing Lagrangian from these?
We now have the ingredients necessary. All right, so the Lagrangian of the SU5 gauge field theory. Under the unitary transformation with the right here.
How they move? How they move under this gauge field? The motion. So Lagrangian, you need Lagrangian to find the equation of the motion, right?
Yeah, gauge field obeys the transformation rule.
For the dynamics.
Right. So this times x, which can also be written as this, right? Where is the vector field operator. Transformation of the wave function in the representation is defined by remembering that the 10 representation is based on the 5 representation.
I do
Wait.
these things, but in a different way. That's all.
Yeah, probably.
Like you
I
are
don't
doing.
know.
Like you.
I'm not really using an awful lot of this kind of
Yeah.
mathematics.
I go in
Although-
a different direction. I use gate field and all, but
Yeah.
very different.
Ah, okay, yeah, understood.
But more on the time aspect. I think
Well, yeah. See, this is it. This is why I wanted to look this up, because I have an embedding of all the particles of the standard model into the 120 cell. Is that? Oh, I don't know if I have.
One way is to code all these stuff, and let that Python or what will take over.
Yeah. Well, there was some stuff that I had, but probably not.
Yeah, in my the next paper, I'm using the Python code. I mean the one we did, very similar to the one with Emery. So I'm putting that in there.
I've been creating these graphs of.
Yeah, for signal. See, he did that for the sinusoidal wave, but I'm going for the abstract signals, and I'm using that. And surprisingly, it is when I combine that different abstract things, it is kind of simulating that the signals. So it is quite interesting. I mean, there's a lot more to do, but shows initially some promise that from the abstract thing of the signal pattern, you can create signals that we see, the cosmic microwave. I eventually want to show how the cosmic CMBR and the gravitational wave combine together to produce a lot of the signals that we see.
Oh. Okay, would there have been gravitational waves back in the time of the CMB?
Yeah. So you have the photonic component.
What's generating them? Is it what generates them?
Okay, the micro black hole will generate the gravitational wave.
Oh, very, very small.
And the 0 point.
Oh, do you mean like? Oh, okay, so are you talking about the fluctuations in the CMB that we see?
Yeah.
Happened when the universe is very small, and then the micro.
Yeah, the 0 point field. Yeah, the 0 point field is the CMBR. 0 point field eventually creates a CMBR, and the micro backwards eventually will create the gravitational wave.
Right. Well, could you have micro black holes inside a singularity?
Yeah, but see, I'm right now. Eventually, once I prove these, once I get over this, like another 3 or 4 papers, then I go into the idea: is the micro black hole a monopole? You know, are they the same? That's what I'm trying to.
I don't think so. I don't think they're very different.
Yeah, but they are connected in some ways. So I'm trying to.
Oh, yeah, maybe through some way. Yeah, for sure. Then also,
they're not the same. They're not identical. But I think when the micro backwards combine to form like a like a dipole, they become because they get compressed, they form a micro backwall in that process. And then 0 point. So they produce 2 things. When the 2 monopoles, north and the south monopoles, come together, they could be producing, 0 point field and micro backward. So they dissociate into these. So that's how the gravity comes.
You're at the beginning of the universe, yeah? And
yeah.
Pure energy floating around. And
yeah.
The universe is expanded, I don't know, like some small amount.
Yeah.
Okay.
The universe.
But you don't have matter, right? You just have pure energy in a ball.
Yeah, it's a noise. Just a noise.
Wait a second. Let me ask the question I'm going to ask.
Okay, go ahead, please.
Right. Is that pure energy able to collapse into micro black holes? And if it did, would it not happen all across the surface of the ball, the expanding ball? And then if that happened, would anything really expand? Or do you know what I mean? I suppose so basically you're saying it's like a really high, well, a particle accelerator, but there aren't any particles yet, right? Because there's anything we'd be talking about, there'd be no at those energy levels. There's going to be no, the forces aren't even going to be present, are they? Well, it's going to be some sort of unified force, I think.
Yeah, actually, they'll be very low signal, like a dark matter, dark energy type of thing, where they are like noise, like a superfluid, noisy superfluid, you know. So
superfluid, yeah, okay. Yeah.
So it's a very chaotic, but they are not real, you know. They are they're just fields. So and then if it's MRE, there should be discontinuum energy fields, you know. So eventually we'll come to the what I have done with MRE. Will also will account for a lot of those things because they are not continuous. That's why we are getting the quantized aspect, and that quantized aspect of that field is what is creating the particles and everything, you know. So they are not continuous; they are discontinuous. So that's the whole.
Well, actually, I don't know if you watched recently. There was an interview with some person whose name I've forgotten. I think he works at Harvard. He's a professor there or something, and he was so it's on that channel, Kurt J. Mungel's Theories of Everything. And he was talking about how recently. Yeah, give me a second to remember. So you have you know, you have. I think the title of the video or the thumbnail is. We'll give this a second. It's trying to do some calculations here, but it should produce something in a minute. Well, it was called Hilbert spaces don't exist. So he had all of these sort of thoughts and points that he was making that you know, you represent the particle interactions and the waveform, you know, the psi waveform as a continuous field that's differentiable using Schrodinger equation and all in these n-dimensional Hilbert spaces. And then he was saying, well, no, we shouldn't do that. We should use something more like a Markov chain process, which is interesting because that's kind of similar to what I've been using in terms of Q-learning to do different, you know, to simulate gravity, which has been ongoing in the background. I'll give you updates on that at another later stage. But
I do agree with Sean Carroll about the conda and the fields. You know, I think everything is when you combine the fields are not really continuum. They are not continuum fields. They are condized because of the presence of the monopoles. So the fields get disturbed. They are not continuous. So they do have step functions, whatever you call it.
Yeah. So this was it. He was just this person whose name I've forgotten was had some idea that you could use what are called indivisible. I think they're indivisible processes or something like that. Mm-hmm. And basically, you start at a certain point, and then the system evolves based on the Markov chain process, and then. But at a certain point, it collapses back down again, and then starts to evolve again. And these points are like measurements, but also like entanglement. And the way he put it all forward was, it basically made the whole thing about quantum mechanics sound so boring, and also like he'd like figured everything out, and it was just really, really boring. And, but it wasn't that at all. It was just the way the interview was conducted and made it. That's how it was, you know, how it was related to everyone. But when you really start to dig down into it, well, he's still talking about entanglement. So that's spooky action at a distance or whatever. So that's still weird. He still didn't really deal with like things like, okay, so there's the collapse, but you know, he just renamed things in quantum mechanics using a different system and said, I solved everything and it's all boring. And it's like, well, no, actually, you didn't. You just renamed things and kind of made things more interesting because now people have another tool to look at the results. And then they need to be interpreted properly. And I think this study is quite new in divisible processes. It's only 2 or 3 years old. So he's interpreting the results of quantum mechanics through this new framework, but his interpretations could be wrong, you know. So people need to be very careful, wary of people who come out and say, "Well, this means this," and just because I said so. So we need to find out if it actually does. So here is the I plotted the entire 120 cell, and I managed to put the particles for the standard model onto each of the vertices. So all the different colors here stand for, because there's 5 600 cells in the 120 cell. So there's 5 copies of the 600s. Remember, I put all the particles in the 600 cell.
Okay.
Now I've copied it over 5 times into the 120 cell. So each one of these gets a graviton field. So there's 5 gravitons in this This is the unified field of all the particles in the standard model. So you see here we've got like VTL. So that's the left-handed neutrino tau with spin 1 that's bound to the G3 graviton. Whereas over here we have well, let's try a different one. One we can see the right-handed positron with spin 1 bound to the G2 graviton field, and so on and so forth. And you get all of those, and then you take the average of all the points. Now, this is like the best I could do at combining all of the particles, because there's a lot of trouble with the vertices, let's say. Okay, I don't have them here, but basically there's issues with the vertices and how there may be. And this is a wireframe version of the 120 cell. So I could put the particles on that and it would show how they're connected by edges.
Are they chiral? You are bringing in chirality there?
You always ask that question every week. Are they chiral? Well, didn't I just mention right-handed and left-handed?
Yeah, but so I think that, what I'm saying is that what I'm coming to that is that I think it's a chiral universe. That's why it makes it asymmetric. Because if you are chiral, they don't cancel each other.
Well, they would. Right and left cancel each other perfectly.
No, they won't directly cancel each other. You see that they do differentiate in space.
They should cancel each other though, shouldn't they? Because they're completely equal. Right and
no,
left.
But the chiral means the mirror symmetry. They cannot see. You cannot fit. I cannot cancel this and fit right-handed or left-handed. I have something in space still. You see that I cannot totally. Whichever way I try to put a left-handed, right-handed, I cannot cancel them.
Wrong. That's totally wrong. Look at this.
Huh?
Cancelled.
No, but that's not really a cancel. Cancel means it should disappear.
Well, you don't expect my hands to disappear, do you?
That's what I'm saying.
That's what exactly I'm saying. They're completely symmetric. So
if they are not chiral, they will disappear.
1 and -1 are completely symmetric, yeah? And they cancel. Right and left.
Yeah, but they are not see, they are more than 1 and -1.
If I'm rotating this to the right or to the left, if I do them both at the same time, nothing happens. So they cancel.
Well, they form higher dimensions.
Actually, the cancellation is a wrong concept. I
mean, we know there's symmetry breaking, so we know that there's definitely, they aren't actually symmetric in the universe, are they? But they should be, and most of our mathematical representations are always symmetric. If I have a cube and I can rotate it left, I can rotate it right, and those two operations and transformations are symmetric. The difficulty would be to show how that breaks. So for instance, if I'm looking at this screen here, I can rotate this way, or I can rotate it that way, which means that this top left-handed anti-quark with spin up can rotate into another vertex that is a top right-handed anti-quark with spin down. You know what I mean? So there's a problem, or it could rotate into a lepton, let's say, which would be totally wrong, because how can the quark transform into a lepton? So the way that this works is we take all of these vertices and we take the average of the vertices in the cell. So we get the dual representation of this, which is this 600 cell. And then that is not chiral, because we have the fermions here and more fermions here, and then the quarks on this side and the other quarks on the far side. And so that's a spin 2 representation, because if I rotate this into this has color charge, this doesn't, so they don't go into one another. And it's only when this goes back around, and that's why we get a spin 2, and that's why the 5-dimensional representation of the gravitons just goes down to a spin 2 representation here, and that's it. So that's how the unified fields break down into spin 2 representation and SU3 and SU2 symmetry breaking, and that's it. I think that's the answer to the whole thing, really. Although obviously there's more to it that can be worked out. Like on your end, Rajan, you're very into the Lagrangian and the gauge groups, the proper way to do it through algebra and such, or algebraic linear algebra. If you can see how to apply that kind of math to this, I'd be interested to see how you do it. But personally,
no, what I want to do is, from my thing, I want to create a code. So then you have a code. These two codes can be combined because they are too complex to handle by hand. But the code should be code independently. You can verify them and say that they are producing the right results. Then you can combine the two codes, the space code and the time code, combine them together to get the space-time code. And then that will be interesting. That will probably evolve because
once we have the 4 vector, it's going to have time in it. But at the moment, I'm just using Euclidean coordinates. Now, we can also include time. Now, I've stopped sharing the screen, but there are other ways to do it. So later on, we're going to look at how to transform a 4D Euclidean coordinate system into a hyperbolic space-time coordinate system.
Yeah.
But I still have to do that.
The interesting thing I'm coming is that time actually could be a divergence of space. That I'm working out that. So if we can, but it will be in a matrix form. So from classical physics, you can say, because expanding universe, right? So you can say time exists because of the divergence of the space events. The divergence of the space events is what creates the time. So it is continuously either evolving, either expanding or contracting, So this is what creates the time.
Yeah, but I think both Wenzhong and I don't agree with it. The universe is expanding, so...
No. I'm saying that it can expand or contract. So in essence, they may not. May cancel out each other.
Oh, do you mean in terms of evolution of a branching system or something like that? Oh, okay.
It evolves, but also it contracts. So the net result may not be expansion.
Yeah, interesting.
You can think time as a change of the space.
Yeah, the time.
Yeah, time is not not independent physical quantity. It's linked with space. When space change, time has meaning. When space not change, time is no meaning.
Yes, that makes sense.
Yeah, and I think Raja's meaning is like what in my paper I talk about is a spring. The spring it sometimes compressed together, sometimes extension. Like the spring, you have frequency, you have time. It's time. It's just the inverse of the frequency. So
yes.
Yeah. If you use frequency, you can get rid of the time actually.
Interesting.
But the frequency itself is because of the expansion or contraction of the space.
Yeah. It's in the universe. If you think more widely, or think more about all the example. Actually, all the change of the space, all the movement,
dynamic.
It's periodic. It's with some cycles. So that's why we have a frequency. We have time. We count our time based on the cycling time. The one cycle. We use one cycle as a unit for time. Actually, it's periodic movement of the space or object within the space.
Yeah.
Yes. Exactly. So that's the event that's happening. The event that is happening is this contraction event or expansion that creates the frequency. So inverse of that will be the time. Yeah, that's it.
Yeah, the time most basic unit actually is a cycle.
Yeah.
You based on cycle to count your time.
Yeah, second inverse. Yeah, second to the power minus 1. Yeah. Or 1 over second per second.
Per second. Right.
So
and also you talk about for example the electron, positron, or proton, anti-proton, or quark, anti-quark. When they come together, they didn't annihilation. They didn't disappear. Actually, they overlap together. We cannot measure them anymore. Use our own our current technology, but they are still there.
Well, yeah, isn't it the idea that they transform in the like mass energy equivalence, or the conservation of energy kind of thing? So energy can't be created or destroyed. So you have these two.
So when they annihilate, they produce energy.
The energy you cannot create, cannot you destroy them. For
right,
example,
they do create energy, like vast amount of energy. All of the energy is converted, right? All of the mass is converted into energy in this process.
You see, if this is electron, this let's only can see my finger. Why is electron, why is positron? When they are far apart, they have potential energy.
Yes.
They have high potential energy. When they come closer, they gain more kinetic energy. Potential energy change to kinetic energy. Their potential energy become smaller. When they overlap, like your hand, when they overlap, the potential energy is 0. They fall into a very deep well. We cannot see them. But their kinetic energy change to a wave, to a photon. Photon actually is a wave to go away. But the electron, positron, they are still there, deep in the potential energy well. If you give them enough energy, they will gain the kinetic energy, their potential energy change, they separate apart. That's why when we supply energy to the vacuum, we get citron, electron. We also can get a proton, antiproton. Like this kind of they never disappear.
They never totally disappear. Totally totally annihilate.
Yeah,
There's
that's
always
I mean,
some.
yeah. So if you have like a sound of like a frequency, and you're listening, let's say it's in the key of C, and then you have the same sound in the same key, but it's inverse. You can get those two waves to cancel each other out. But the amount of energy in that system is actually, let's say one wave had, I don't know, 5 hertz of energy or something. It would be obviously more than that. And the other wave is 5 hertz. Then you either like have to add those two together or maybe multiply them. I assume it's addition. Yeah, it's addition. And so you'd have twice the amount of energy in the room. So technically when you have this like particle where it's like electron, positron, they annihilate, the resulting photon should presumably be twice as energetic as the two particles were separately. And so I think of the two particles are kind of, I mean, maybe you could say like encoded in the photon field, but maybe not. Maybe it's more like what you're saying, that they're, or maybe you are saying that. Is that what you're saying?
They overlap together. We cannot see them. We cannot use our current technology. We cannot, detect them.
Right.
But they are still there, because why I know they are there, because when their wave come, they vibrate. They vibrate. Sometimes enough energy. They vibrate enough. They will appear briefly, then disappear. Not complete annihilation, but they overlap together, become a state. The vibration is too. The space change is too small. We cannot detect.
Yeah, because they have noise. They become noisy.
Yeah.
So two combined together, it become noisy, but the noise has energy in them. Then you can separate that energy in the noise. Then you can bring back the thing. So in the noise, you have the electron and positron, everything in there. But then you have to separate that frequency, and then you can pull out the photon, the electron, and all that. So noise has all the things in there, but then you have to separate them. You have to cut them or differentiate them. That's what, or resolve them. So the noise has all the frequency in them, but then you do Fourier, like a Fourier cut or something, Fourier transform. So they cut into components. So you get individual frequency, and that individual frequency can correspond to photon, electron, and all that,
Yeah, I'm not sure.
They can combine together or they can separate. This is what's happening all the time. Either they combine together and form noise, or they separate and form signal.
But they could, I mean, you could say, I mean, is the photon, well, I mean, I suppose if they're going to combine together, they're going to annihilate, which would create a lot of energy. And then you could call that noise if you want. It's going to be a lot of light and radiation, all of which is kind of in the electromagnetic spectrum. So it's part of the electromagnetic field. And you could call that noisy, or you could call it like new particle.
It depends on the phase angle.
See, if it is a new particle. But yeah, they both have to have, sorry, go on, Rajan.
Yeah, depends on the phase angle of how they collide. If they're constructive, they can form like a laser, like a highly resonant thing, right? With destructive, if they're out of phase, they form the noise.
Is that true? I mean, do you like? Where's your well, like, yeah, okay. So where do you have proof of that?
Yeah, the Emery Taylor, I'm doing that. The discontinuum thing.
Is it experimental, like results from the Large
Yeah,
Hadron?
you can conduct experiment to prove you can bring two waves and you can have them in phase. When you pull them into phase,
Yeah.
you can create a resonance, and you can have two waves which are out of phase with each other. You combine them, you can produce noise. I think it's possible in oscilloscope.
Well,
Somehow.
we know that, but if you have, by definition, if you have a positron and an antipositron, an electron, those are out of phase. They are, that by definition, you know, so if you were to alter their phases so that they were in phase, they would still annihilate because they're just different. You know, they're conjugates.
Yeah, you can annihilate them. But annihilation produces noise.
As far as I know, you cannot create constructive interference out of antimatter and matter.
Yeah, so it will produce noise. So it will produce noise.
Just, yeah, I mean, yeah, you could call it noise, but
see, there are different forms of energy. Noise is like entropy, you know, and the other one is, if they're constructive, they produce energy. If they are destructive, they produce entropy.
Right, but matter and antimatter aren't constructive. They are always destructive.
Yeah, so they'll produce entropy. They should produce entropy.
Okay. Well, that's interesting. So, Wenzong, what's going on with you then? You wanted to present some research, or
yeah,
or so do you want to take a break?
Yeah, we can take like 10-15 minutes break and come back.
Okay, and then Wenzong will
do his presentation.
Great. Okay.
Sounds good. Thank you.
Covered it because it's say that they discovered it.
Okay, you hear me? Hello?
No.
Can you hear me?
Yeah.
Yes. Okay, great. Anytime you want to start, Wenzong.
It's Roger
anything-
come back. I just give a very brief, simple, introduction of the work I have done up to now. So will Raja come back?
Yes, we'll wait for Raja. Okay.
Yeah. Yeah, so you okay. Oh.
Are you there already? Oh, okay.
because it's been there.
Are you all there?
Oh, okay.
Oh, Wenzong. Okay.
Okay.
Okay. So you can, yeah, I think Christopher should be back soon. Then we can-
Yeah, yeah.
So this is, you are going to present your, about the, how you combine the Planck constant and the Hubble constant. Is that the one or?
Yeah. I give a brief introduction of my recent, oh, where is,
Oh, Christopher went off, but he had to come back again.
yeah.
Maybe he has to sign off, then he'll sign back again.
Okay. How are you now?
Yeah, okay. So are you still working there? Can you spend more time in research now?
Yeah, I resigned from the work I have done 18 years now.
Oh, you're teaching? Were you teaching there?
No, I didn't. I don't teaching. So for the past 18 years, I'm doing some research and development work related to defense nuclear.
Oh.
Now, there are more and more restrictions. So I
What
take-
nuclear is that? Is it nuclear fusion? No, not nuclear fusion, right?
Okay.
Is that nuclear fusion?
No, it's nuclear power system for nuclear submarine.
Oh, okay. Yeah, I am just teaching. I'm retired, but right now I'm teaching in schools. As substitute, as a guest teacher, but I'll continue another 1 or 2 years. But I want to develop our thing to go full time if possible, But I'll be retiring, but then I continue with this research, and so it's quite a lot of this. The time aspect is very interesting. I mean, I come up with very very interesting. You may have seen, but I have not put the most recent paper yet in RG. I think I will try to put it there, because the time is a tensor, so that's a very interesting thing. It's not a scalar that we use, so that how you find the future. The future is like a wave function, a time wave function, the tensor waiting there. Then it collapses to some value. That's how we get present to future and moves on. The past, present, and future. So it moves on by that. So certain things decide which way to go. So that's what interesting thing is. So then eventually, once I prove this, then you can figure out what is deciding it to move to the future. So that's interesting thing. I think Christopher is back. Is Christopher back?
Yeah.
Oh, okay. So I think Wenzong, you can go ahead, present your.
Okay. My most important finding actually is intrinsic relaxation frequency or intrinsic relaxation time of the whole observable universe. Actually, if we think a bird fly in the air, or if we think a fish swimming in the sea, actually, when the fish or bird fly from one place to another place, actually, in the path of the bird of the fish, the air or the water need a time to come back to original state. That take time to recover. This recover actually is not local. It's whole atmosphere or the whole ocean. I think when the light fly in the free space or vacuum, actually, like the bird or fish, when the photon, flight past a place, this place need a time to come back to the, original state. That is the intrinsic relaxation recover time or intrinsic relaxation recover frequency. So that is from a mechanical point of view, we can think about this. That's the first few paper I published. Use the harmonic oscillator model, spring model, to model the photon to propagating through the free space. So you use the viscous friction to calculate the intrinsic recovery time or frequency. So that is actually it's the Hubble constant, 10 to minus about 10 to minus 18. Frequency is 10 to minus 18. The time is 10 to minus 18. Very long time. The whole observer universe recover to the before the disturbation. Now I use Maxwell's equation, get the same, exactly same results. Because when the electromagnetic force or field are long range force or long range effect field, actually, if we focus on one cycle of the alternative electromagnetic, field change of the photon, this electric or magnetic field change actually affect the whole observer universe. Within the whole observer universe, there are lots of, lots of pairs of charges. Actually, this alternative field change affect all the pair of charges within the observer universe to trampoline. So the trampoline is very small, very, very tiny, but we can imagine, we can foresee this effect. So when the photon propagate from one place to another place, cause some change. This change need fully recover. We can use Maxwell equation and Pyongyang's theorem to calculate. Again, it is Hubble time or Hubble frequency. So I use these two methods to get similar results. Another simple method you can use is you use the photon's angular momentum, the Planck constant equals to equivalent mass of the photon multiplied by the speed of light and multiplied by the wavelength. mc lambda equals to h. If you do a differential, in one end the h is constant, you get 0. In another end, actually c is constant, you can take it out. You get actually the m, just the equivalent mass and the wavelength change inversely with each other actually. So if after you do the differential, if you integrate them, actually you get a relation. From this relation, if you assume the mass reduction equals to the the mass reduction ratio equals to the wavelength increase ratio. If you equal to h, the Hubble constant, you get similar, the photon wavelength change, mass change with the photon wavelength change. If you multiplied both sides by the light speed square, you get energy change with the photon wavelength. Actually, you get the redshift, cosmic redshift, the exponential relationship as well. So from this, you still can calculate every cycle of the photon propagating. You get energy dissipation, Hubble constant multiplied by Planck constant. Use 3 methods, you get exactly same results. So, and also this especially the viscous friction method, and also the electromagnetic method, you all can see they do not affect the direction of the light or photon. You do not cause blur image problem like originally when Zivik proposed the tail light hypothesis. The people do not take this hypothesis because they think if light lose energy collision with something, then it will change direction or become blur the image of the object. But now, if it's a friction, viscous friction force will not change the direction of the movement, will not cause scattering of the light, so will not cause blur image. And if alternative electromagnetic wavelengths affect the whole observed universe, because both sides of the whole observed universe, if you take the scale of the whole observed universe, actually the charge or the mass, actually they are equal to each other. So when the electromagnetic wave propagate, will not change direction as well from a large scale, but in a small scale, for example, near the sun, because locally two sides, the mass or electromagnetic field slightly different cause some light bending, but in the end, you average out the whole path of the light. Actually, this bending, sometimes bending this way, sometimes bending that way. If you average out, actually it's still a straight line. So both way, we can approve actually light or photon lose energy during propagation. So that is tail light you know, mechanism, not space expansion. So from the very fundamental level, we can prove it's you know, energy dissipation rather than space expansion. The space is kind of medium, like you mentioned, is super flat medium. It's a super with something similar property like the super flat helium. You know, the super flat have properties. They try to fail everywhere they can. You know, they try to make everywhere the same density. So that's why we see a very flat, uniform universe. So, but in somewhere like the sun or the, you know, the center of the galaxy, because they're high temperature, they become vaporized. Actually, when vaporized, the density become smaller. So the other part of the superflat subtle things try to, you know, move towards this place to fill the, you know, fill it up. The vaporized, you know, space, or we can call it, or superflat medium, when they vaporize, actually they become the light. They produce a dynamic equilibrium and circulation. I'm still thinking about how can they condensation to matter. Actually, I just, you know, before the end of last section, I mentioned when two things go together, so they didn't disappear, but they fall into a state with very low potential energy. So when they fell into a very deep potential energy well, so all other superflat will fail to this well. So, but the condensation mechanism, I'm still thinking how to solve this. If we can solve this, then we can produce a theory, you know, all the matter, the normal matter, you know, the light and the space, free space, we can understand. We can understand this whole, you know, dynamic equilibrium and circulation. I think that's what I'm doing now. I try to develop some kind of theory to understand this grand dynamic, you know, circulation and equilibrium.
So if you want to present anything, do you want to show anything? You can go. If you want to present anything, you can go to present.
I haven't prepared
Okay,
any,
okay.
you know, display. So
Okay.
because I haven't joined this meeting for a while, I want to listen to what you guys are discussing. So
Yeah,
you
I
asked
think
me
we
to
understand most of it. What you are saying, you know, I kind of understand what you are saying. You know, in general, you are describing quite well. So one of the things is that you said that the superfluid, the evaporation occurs. So that evaporation makes into photon, right?
Yeah.
Okay, and there is a space created. So from some other place in the superfluid, it try to fill that space.
Yeah.
So then it creates the that's very similar to what I was kind of. I'm also going very similar thing. It's not exactly the same. So the evaporation, yeah. So that becomes the CMBR, for example, And the other one, when it fills in, it creates the gravitational waves, which means that that's the idea of micro black holes, and also the idea of 0-point field. So it creates so when it evaporates, it creates a 0-point field inside the superfluid, right? So that's what the CMBR is. But then when it moves, it creates that micro black hole. So you have, see, what I'm saying essentially everything is time and gravity. Time is one way, gravity is another way. So it creates the time when it starts flowing, it creates the time. The flow, time is the flow. So that it creates the time, and then the gravity is created out of that. So see, my new paper says that actually the conserved quantity is time. And I prove why the energy is conserved, but only the quantum energy is conserved. The complete energy is not conserved because it becomes noise. In the superfluid, you have almost infinite thing, but energy cannot be infinite, right? Actually, so if there is infinite energy, there is no question of conservation of energy. You see that? So it contradicts each other. So the superfluid is an entropic. You can say entropy exists there, and that's where the conflict is. When you equate entropy to noise to matter, so then you need dark matter. You see that? So it's not very simple in that way, but you can come very close to that. Like I said, the constructive interference, destructive interference, two waves come together, and we can actually prove. One time we can bring an oscilloscope. We should be able to do in computer, right? We can create an oscilloscope, software oscilloscope, and then we can do this experiment. When we in phase, when you bring the two waves together, it should form a resonance. And when we out of phase, two waves come together, they destroy, and they should create a noise. We should be able to simulate by an oscilloscope in our computer, and then we can show here. I think some point. I think probably even Christopher should be able to do also. He knows the programming.
Yeah, that's interesting. In my view, the flow of the superfluid medium causes the gravitation force.
Yes.
The gravitation force actually from the flow of the superfluid medium.
Yes.
Yeah.
So it's just like gravity. See, so you have you saying it's like an empty space creates empty space, right? So then it flows there. So it looks as if it's always it's attraction by gravity. Everything flowing. So it looks like gravity, but actually it's creating empty space because of the evaporation process.
Yeah.
So that's an interesting thing. The condensate, evaporation of from the condensate, it's like condensate, the superfluid. The evaporation of the condensate then creates that hole, and that hole or the empty space acts like gravity, attractor.
Yeah.
That because all the other things will flow into it. So it's like a micro black hole. It's like micro black hole when everything starts flowing into it. So that's what gravity is. So gravity is not a primary thing, but it's a secondary effect of the.
Yeah, it's a secondary effect. Yeah. I
so
agree with you.
Yeah, I think we are all coming to the same, very similar things. It's an interesting, very important concept. I think we are saying that gravity is not the thing, but it's the secondary effect because of the evaporation of the condensate. And why does the evaporation of the condensate occur? That's the next step.
Yeah.
So everything is like randomly fluctuating, right?
Yeah.
And then why does that create that evaporation process? And I think I have come up with the following thing with the discontinuum field that in the local thing, you can actually eventually prove. We don't have proof yet, mathematically prove any random process locally, you could have a distorted field, a distortion process. And this distortion field that creates is the one that is that that evaporates. So when it creates that distorted field, locally, then it evaporates because it has higher thing. If you calculate the potential energy, kinetic energy, it has a higher energy. So it's like a bubble. It's like a bubble that forms in the water, right? When you heat, so the bubbles start coming up. So it forms like a bubble there, the distorted field, and then it comes up, and then it creates a hole there, like you said. And that hole, everything else from other side start flowing into that hole. So that's how you have the whole dynamics occurring. But mathematically, I think it's possible. It's very difficult at this point, but I think mathematically you can do algorithm or equation of a random process, and in that random process, when you simulate, you can even simulate using a simulator a random thing that is happening, and at some point it will create a distorted field locally. And the element could be the monopoles. You see that? So the monopoles are what is the agent behind that. So there has to be an agent that creates that kind of local distortion or asymmetry or whatever you call it. So the what happens is the monopoles, when they're separated, the north poles can go, south poles can go, but at some point during the fluctuation they come together, and a group of them come together and they start locking in, and the lock in they produce dipoles. Like John says that it's a horde. So it's like a horde it creates and it locks in. So the dipole is locked in, and that dipole then then that energy is released because the monopoles are immense amount of energy. When they combine together, energy is released. So you have a high energy at that local region. That creates the distorted field, which has very high energy. So when it has high energy, it will start to evaporate, like boiling of water or whatever. And that when that evaporates.
I was just going to say, it's interesting because you're talking about the gravity from like a thermodynamic, fluid dynamic kind of point of view. Superfluids. So previously I'd done work on the concept that gravity might be a kind of tension around objects in a higher dimension, and then. But I'm just wondering, so if let's say I was correct in that assumption that it was a sort of a surface tension, sort of meniscus kind of flowing in towards an object, then if it was a superfluid, I know that some of the, I'm not clear on all the properties of a superfluid, but I know that it has zero viscosity. I'm just wondering, I'm assuming viscosity has some connection to surface tension. And what is the surface tension of a superfluid? Is it zero? And if it is, then that might be a reason to rule out the sort of underlying superstructure of gravity and of space-time as being a superfluid. I don't know if you have any thoughts or comments.
Yeah, it's quite interesting, Christopher, the idea of viscosity, because that's what exactly Maxwell was dealing with. The problem of ether has, if you have ether, it has viscosity. So there is no way, and it makes it impossible for it to have a universal, it cannot move around the universe because it will lose energy very fast. So that's why the idea of a vacuum came into being. And the vacuum, there is no problem because there is nothing, so there is no viscosity. So the light can travel infinitely at speed of light, constant. But it will be, but of course, he had proved that the vacuum
it will like a vacuum permittivity and permeability, which seems like a viscosity term, and then also
minimal.
Well,
it minimizes. Yeah, minimum viscosity. So the viscosity is at the minimum in vacuum.
Space is supposed to have like zero. With space is kind of supposed to have like zero, properties.
Well, you can say that, but you can say minimum. The minimum we can take it as zero. But is it really zero? I don't think so. I don't think.
In my view,
This is
if
the kind of
you're
debate. I mean,
in my view, if you focus your mind in the vast free space far from the, for example, from the sun, from the stars, from the galaxies, actually in the vast free space, the superflood actually they propagating every direction the same speed, light speed. They are every direction is the same. So only when you near the center of the galaxy or the sun, they are slightly, preferential, flow. The preferential flow is very, very small. But, in the background, all the superflood medium, they travel every direction in light speed. So, like in my previous few paper, the superphoton, the elementary superphoton, they travel at light speed. They are very tiny, but they travel at light speed, actually in every direction.
yeah,
So, I mean,
just think, I suppose the point is about viscosity and, well, if you have a tired light theory, you're talking about light and a certain amount of friction against space. So if space has, a property of friction, then we would assume that viscosity, it would also have a property of friction with itself, wouldn't it? Which would be a kind of viscosity. So you'd be, from your perspective, from your theory, you would have to have a certain amount of viscosity in space, and then that would seem to contradict the superfluid element, wouldn't it?
It's very extremely weak viscosity. Even the superfluid helium, the viscosity is not zero. Even the superconductivity,
right.
the resistance is not exactly zero. It's very near zero. So people for our human scale engineering, we assume it to zero. We can do a calculation, get a good results, but they are not zero. If you put a superconductor array there, after a long time, the energy, the current will disappear because their resistance, the resistance is extremely small. So the similar thing as
but maybe it does also have a certain amount of
there are already experiments in there are already experiments in the superfluid helium. They can measure the viscosity. It's extremely small, but it's not zero. Now, this year, a paper just published. They invent a method to measure the, viscosity resistant force of the vacuum in a laboratory on Earth. They claimed they successfully measure the frictional force. So this is the first paper said, experimentally they can measure the frictional force of the vacuum. Before this paper, there are quite a number of papers. Theoretically, they affirm in the vacuum there are frictional resistance.
Yeah, that makes sense because the vacuum is not empty. You see that? There's always particles popping in and out in the in the vacuum. So the viscosity is not zero because of that.
Only thing is because it's so so extremely small. If
Yeah.
we assume it is zero, in lots of engineering problem, we got good
Yeah.
results. But scientifically, more rigorously, it's not zero.
Yeah.
Either the
Yeah, but so I wonder. Yeah, so I was just going to say, how do they know that they're testing a real superfluid like at a perfect temperature, or could there be slight temperature fluctuations in their experiment which would lead to some viscosity? Like what I'm asking was, would a true superfluid have zero viscosity? Like, let's say even in the abstract sense, even if it wasn't able to be created in reality. And then would that also suggest then that if space is a kind of superfluid, that it's somehow like not an entirely perfect one if it has a certain amount of viscosity?
The pseudo superfluid. Yeah, the reason
Yes.
is that if it is zero, right? If it is zero viscosity, the universe would not have formed. If you think about
Yeah.
that.
Oh yeah.
Yeah,
Interesting,
if you see the background microwave radiation, the temperature is 2.7 to 5 or 6, very very stable over the sky when they measured. This is another sign. Actually, they are kind of super fluid, filled with
Right.
all the observer universe. And they are not only super fluid phase, but also, the light, the normal light we see actually it's vaporized phase, like Raja said, like a bubble. So there are two flood model. If you see some published paper about superfluid helium, they mentioned about this two-phase flow as well. One phase
Oh.
is absolutely superfluid. Another phase
Yeah.
is some bubble, some helium gas bubble. So
Yeah.
the similar thing like this, the light we see, the normal light we see, is a kind of bubble. It's a vaporized bubble, and the underneath is the superfluid. So there are two-phase flow. Between the two-phase flow, there are extremely weak frictional force.
Mm-hmm.
Yeah, Corrado Massa. Remember, Corrado Massa has very similar thing he presented, and he has interesting. We had.
He has his theory of minimum energy.
Yeah, minimum energy. Yeah, that's interesting. Very similar to what Wenzhong is saying.
Yeah, very interesting. Either use mechanical modeling, use spring model, the harmonic oscillator, or use the Maxwell equation, use the electromagnetic autonic electromagnetic method. Both method you get same results. The energy dissipation of the photon every cycle is Planck's constant multiplied by Hubble constant.
Oh yeah.
So it's quantitatively derived. Very, I think the whole derivation process is very rigorously. I don't think there are problem with these two methods of derivation of these results. The only thing is now the mainstream power is too strong. They do not want to the challenge will to be published in the top class journal.
Yeah, actually, we do the. I think it's good to conduct this simulation experiment with an oscilloscope.
Yeah.
I think people will be more willing to accept that because they see the results. They cannot deny the underlying concepts. That's we can prove them with a simple oscilloscope. we can do in a computer. We don't need to do
Yeah.
lab.
The underlying, mechanism is very solid.
Yeah.
Not
Yeah.
like the space expansion, Big Bang, all assumptions, so many, imaginary concepts.
Yeah.
Yeah, they are the
Never can be
assumption,
proved.
See, finally it all comes to certain assumptions. Like Christian also is pointing out I space, that there is no zero, it's all multiplication. So it's all, we are all coming to very similar conclusion, because original thing, we are, our assumptions, I would say minimal. We are trying, see, we cannot say zero assumptions. We have to minimize the assumptions. There will be some assumption, like even if you put a monopole that creates, that's an assumption to some degree, but it's a valid assumption. You have to justify that assumption, then it's okay. But a lot of these people, a lot of the other things like expansion, they may have assumption that's not validated or justified, So that can be falsified, or that can be put into question. So the falsification aspect is very important. Falsification of the assumption. If you can think about it, maybe one of the key things we have to consider. Yeah, I think Christopher dropped out. It's okay, he will come back again. But yeah, so I think that's a very important thing. If you think about falsification of assumption, that may be a big thing. And so we can do the simulation experiment, and you can prove a lot of things, because you have a thorough math also, and I have on time. Yes, so I think we can put together a code, and then we can bring out that oscilloscope thing, and then show them. I think the world will start to see the light of the day. They will start seeing, oh, there's something to it. Right now, they don't see anything. From our thing, it's just theory. They think it's a conjecture or theory, hypothesis. There is no experiment. There is no proof. But the simulation experiment is partially a proof. If we can.
I think the frictional resistance of the vacuum already been proved, published early this year, and we can design a method to measure the electronic resistance of the vacuum. I think that is very easy to achieve use current technology.
Yeah, you can do in computer. You can do computer simulation.
Yeah. We can do.
You can create a capacitor. Capacitor, and you can do a capacitor and a resistor RC circuit. You can create, and you can create the circuitry, and you can simulate in the computer.
The simulation is more easy to do. I mean, even in the laboratory, it's not difficult to use current technology to measure the electronic resistance of the vacuum. It is achievable use current technology. But I do not know where we can get funding. If we get funding, we can build experiment to measure it. We definitely can measure value. So it's 10 to minus 29, the conductivity. If the resistance is 10 to 28 ohm, very high resistance, very low conductivity. But it's a a measurable scale use current technology.
Yeah. So one of the things you can do is you can have a vacuum pump, and then you can start low vacuum, right? And then you can measure this resistance using the RC circuit, and then you pump it down, and then you can get a continuous curve or points, right? So we get a curve for different vacuum level, we get different resistance, and when you extrapolate to zero, see whether then there should be intercept. It should not be zero. there'll be intercept. That is the resistance of the vacuum.
Yeah, yeah.
So it's a very simple. Yeah.
Even the best vacuum in the vast free space, there's still hydrogen, helium, and
Yes.
also electromagnetic fields, and also gravitational fields.
Yes.
It's not empty. Yeah.
See, for example, I do electron microscopy. We have to get a very low, very high vacuum. So that's like 10 to the power minus 8 or something like that of torr.
Yeah.
So we pump down. We use different pumps. We use mechanical pump. Then we use diffusion pumps. There are very high level ionic pumps, vacuum pumps. So we have to use all. I have used that. Then pending trap and things like that. You use that. So that way you can increase the vacuum level. And I'm sure LHC also they have to create that vacuum, right? So they use all these techniques to create the vacuum. I actually had courses. I did a lot of courses. We had, it's a regular course with grade and everything for vacuum. How to create the vacuum technology, different pumps. Even in undergraduate level, we had courses, and it's very extensive. How much? It's a complete calculation of what each one has a limit. How much? Like mechanical pump can go up to like 10 to the power minus 3 torr or something like that. But then after that, you have to use something like a diffusion pump, and then after that, you have ionic pump and so on. And there is few more other types of pumps and techniques that because what happens is when you go to very high vacuum, you have to worry about the vessel or the container, because the walls will start to
release something.
Release atoms. So you have to have a special technique to prevent that release of the atoms from the wall. So there are many things you have to take care of to create that high vacuum.
Yeah, I think these two directions are very exciting. One is design some experimental technology to measure directly the resistance or the conductivity of the vacuum. Another one is the computer simulation.
Yes. So we can do computer simulation. For us, it's very expensive. We don't have that kind of money, but we can do computer simulation.
Yeah.
That's a good possibility. That's something we can think about, a project we can think about. We can do, we can start working on that, and in 1 or 2 months, we can start simulating,
Yeah.
In our YouTube, it's whenever live broadcast, we can show.
Yeah, like another interesting thing I found is I actually found a paper to try to measure the conductivity or the conductivity, the resistance of the superconductor.
Yeah.
Actually, the superconductor, the conductivity very high, the resistance very low, but not zero. They can measure an exactly value. So
at the absolute temperature, close to absolute temperature. Again, it's not absolute temperature, 4 degrees absolute.
Below the critical superconductive temperature, they did some experiment to measure the resistance. Extremely low, but it's not zero.
Yes, that's what I come up with. I think I discussed in one of the earlier the session YouTube. I discussed with Christopher about that. That I have a paper that's coming up. The two ends of the states of the universe. One is vacuum. The other one is superconductive. So I approved from absolute abstract signal theory, signal physics, that actually when I manipulate the equation, the abstract thing, I get the limit T tends to infinity, it becomes vacuum. The limit T tends to 0. The T means the absolute temperature. tends to 0, it becomes superconductive. So these are the two limits of the universe. So the universe oscillates between the two states, essentially.
Yeah, that's very interesting.
Yeah. So that's why these 3 or 4 papers are very important. They'll lay the groundwork, and based on that, then your thing, everything we can put together after that and do the simulation experiment. I think we can do it probably beginning of next year. We should be able to start doing the simulation experiment. And then, of course, Christopher has extensive IT programming things, so he can program that. I think that the basic oscilloscope, the software is available online, so we can pull out, we can start working on. Then we have to do coding and manipulation of the code. I don't know whether AI can help in that, but we can try, because the AI can help in some of the things. So I had to find out where the AI program can pull out the oscilloscope experiment. That will be interesting, because we can ask the AI to do an oscilloscope experiment and see what it does. Whether it can pull out an oscilloscope and do the simulation, we don't know. But we have to do ourselves, I think, because I don't think AI is still it doesn't have the capability. It can do the text, but it cannot do graphics, So it probably cannot pull out the oscilloscope. But separately, we have to do it from from Google or something, and then mix all these together, and then conduct experiment and say, okay, 2 waves with 0 phase angle. What happens? So it will show the synthesis of that. Then 2 waves come together and they have out of phase. What happens? So it will give output. So from there, we have a way to change everything, the parameters, such that we can start figuring out. Then now the other simulation is more difficult, but we say, okay, what happens in a vacuum? We simulate the vacuum. Then what happens in a vacuum? They are again, when the waves come together, what happens? So the permittivity, permeability, and the viscosity, all this come to picture. I think the permeability and permittivity together can we should be able to find a relationship to viscosity. Viscosity is, I think, is connected. We can connect to permeability and permittivity, and then we say, okay, what happens when permeability becomes epsilon 0 and mu 0 for the vacuum? What happens to the the viscosity, and what happens then to the wave synthesis? So then it will be interesting to see that how the vacuum is not, when we extrapolate with the vacuum, with the higher and higher vacuum, then we say, okay, there is still some resistance still there, which means that the curve doesn't go to 0, the origin. There's an intercept. That intercept is that vacuum resistivity, which may be very small, like you said, 10 to the power minus 2 or whatever. So that will be a proof. Then we can publish together that, and that will be a very important proof of the whole thing.
Yeah, my calculation based on the current, Hubble constant as around 70 to 71. The conductivity of the vacuum is 10 to minus 29 Siemens per meter, I think.
Oh, is it a torr? Oh, no, sorry. That's the resistivity. So resistivity is
the resistance, electric resistance is 10 to 28 ohm, very high.
10 to a minus 28 ohm?
No, but not minus. It's if resistivity resistance is 10 to 28.
Oh, 10 to the power 28 ohms?
Yeah.
Wow, this is very high. Very high.
Very high, yeah. The conductivity is very low. It's 10 to minus 29.
In what? What is that? In vacuum?
Yeah,
Oh, the vacuum, the resistivity is very high.
resistance is very high, 10 to 20
Oh.
ohm.
Oh. That's why the charge cannot move, huh?
Yeah, because the resistance too high.
Ah.
But it's not zero. The conductivity is very low, 10 to minus 29.
So that's why the charges don't move. But how the photons can move, because the conductivity doesn't matter for photons.
Photon actually is oscillation. Oscillation, like we previously discussed, in the free space, there are lots of overlap. Electron, positron, they overlap. They stay there quietly. If the photon like a disturbance is force move them, separate them apart to a distance, then they come
So that's
together.
phonon, right? The transverse will be longitudinal, right? But the light is longitudinal wave.
Yeah.
But the sound is transverse. But in the vacuum, you cannot have transverse waves. You cannot move the sound. Sound cannot move in. You cannot move the sound in vacuum.
Yeah, but
Because
you can polarize the free space, because it basically is composed of some matter antimatter particles. They overlap each other, but when you have light, alternative electromagnetic wave, they polarize the matter antimatter charge. Then they try to, after you polarize them, they need to recover. So that's why we got a intrinsic.
so the vacuum is polarized. It will polarize the vacuum. You mean?
Yeah. Yeah, the electromagnetic wave propagating through polarize the free space. Yeah.
Yeah, that's very interesting. Yeah, that's we can do these experiments. I think next year we should do. After the new year, we should start thinking about project, experimental. Simulation project. On computer simulation of these, and then we can actually prove experimentally or simulation wise. That's a kind of experiment. The computer experiment we can do that, or software experiment you can call it, and you can prove that. I think then people have to start accepting it. See, once you show the experimental results and they are reproducible, then they have to publish it.
Yeah.
So I think that's where theory you can say this and that. That's what they say. You can say this and that. You can prove anything. But when you do experiments, then it's very clear. It becomes very clear, and they cannot deny it. They cannot deny experimental results if they are reproducible. Somebody else does it somewhere else, same thing, and they get the same result. Then that's what it is about. Publishing. So yeah, we have to do something like that next year. So that will be our focus. We'll do, because I think a lot of the theory I have done. Essentially, I have covered everything. I need a few more papers. Then essentially, I would have covered the main aspect of the theory, and after that, it's just proving it by simulation or by experiment. A lot of it. There will be like 20% still left. 20% theory. We have to continuously change. The theory will change, but not 80% of the theory will be done. Only 20%, of course, will change depending on the results. Because there are some gray areas in the, what exactly is like this is very strong conjecture about the superfluid, like you said, and what I said also, that somehow the local distortion field creates evaporation, and then it starts the whole process, because then you have a hole or empty space, and that pulls all the things together, like in gravity. So then the gravity becomes a thing. But the gravity is initiated because of this evaporation process, which is caused by the distortion, and the distortion in the random fluctuation of the superfluid. So I think when you put them all together, that makes sense. I mean, they all add together. They don't falsify each other, so they are separate, and they are pretty strong conjecture, that is.
Yeah,
But
the majority of these ideas are already scattered in the published. I published 7 papers in Canada Journal Pure and Applied Science.
Yes.
All these ideas scattered into these 7 papers. But now it's time to gather them together, and including some of your guys, ideas, then make a very systematic theory.
Yes, exactly. So we can unify them, but also, the problem is Canadian Journal is very good, but the mainstream doesn't accept the Canadian Journal.
Yeah, you are right.
That's the problem, because they are physical review and top, other papers, physics of the dark universe, kind of like that. They are all they are considered to be the mainstream, but I can question that, because they don't publish really breakthrough things, because they are very, very parochial, because they don't want to dispute about quantum mechanics or general relativity. If it disputes about general relativity, say like speed of light, you can have superluminal thing, they will totally disregard that, because Einstein, the general relativity says that nothing can exceed the speed of light. So, that's the basis on which it is based on. And the quantum mechanics also has fundamental basis in the sense that, it's essentially a Schrodinger Hamiltonian. So anything that is not conducive to that, it doesn't conform to that kind of theory. These two theories, they will totally disregard that. They won't even consider to peer review. They won't even review. We send it initially. They'll say, okay, we don't, we cannot review this. So
the mainstream, they already produce the kind of system.
Yes.
They try to, try to compress the challenge view out of the mainstream journal.
Yes.
So similar, like Gerbani or Galilei, when they when they produced the solar center system theory against the Earth center theory, it's very difficult to break through the mainstream protection. It takes
the only way experiment, like James Webb telescope, for example, is showing that. They cannot deny that what it is showing.
Yeah.
So those kinds of things.
But now I'm thinking the tipping point is not far away. So the space expansion, Big Bang, cannot survive long. So many evidence, point out they are wrong.
Yeah, they say that everything started with the simple seed, very high dense. You can call whatever black hole, whatever very dense point, and everything expanded from there. That's what, and then creates right now the black hole is kind of accepted. So it kind of creates black hole and then creates the black hole aggregate, create a supermassive black hole, and then creates supernova, and then that's explosion that creates the whole universe. I mean, they are kind of starting to accept that. That was initially, even that was difficult for them. But now they are, because of the gravity, you know, the gravity, they think gravity is a fundamental thing. So if the gravity is everything, you know, compress everything, you get a 1 point. You know, Newton's gravity, for example, everything will go, you know, if there's a chance, it will all become 1 point. And then they say that's how the universe started, you know, it's the inverse process. And because the gravity, because that point has so much pressure, probably infinite pressure, then it has to expand. And so then it creates all those things. But that picture, I think, they say one place, see, but you can have many, many places like that, right? Same thing in many, it can be distributed everywhere. So then in that case, it is not a Big Bang in that sense. So everywhere it is there, but that's a distorted field. That's what we are saying. The superfluid everywhere. Then different places, it has locally it is start evaporating because it creates a distorted field because of the monopole. See, they don't accept the monopole also. But the monopoles, then you need a monopole to come up with the agent that does this job, the mechanism. So then the locally, it creates these points where evaporation and locally creates the hole or empty space. And then it starts this flow. This hole will start to induce the flow of surrounding things into it. And that creates the micro black hole. You know, so that's different from Big Bang. So the micro black holes, now it's possible that micro black holes can combine together. Black holes have the property that they can combine together and they can form a larger and larger, you know, black holes and become supermassive. Is possible, you know, and but that supermassive black hole may not be one place, you know, it can have many, many different places. So there could be more than one supermassive black hole. And then that will make sense because each supermassive has their own supernova and they explode. And then the other things will start interacting and you have complex structure. And indeed, there's complex structure in the universe. You know, you cannot think of one thing that can create all these complex structures. Whereas there are many of them, they combine together, galaxies, they go to each other and they create new things. So we do see that. And that's maybe how the life itself is formed. Because life needs more complex things, more and more high level of complexity. So when the complexity increased to very high level, started creating life. Because our system is so complex, right? The human system or the living thing is much more complex than other things. A lot more things involved. And then we have consciousness coming in ultimately. So the order, see, I use something called the order of the process. Like if you do the chemistry, you see that multi-step process, you have order, right? You have to create order. Order, you know, multi-step process or more than order one. So some other reactions need more than one step. So if it's more than one step, the order of the reaction needs more than one. So then I use the same thing for the process. The process has more than one step necessary. So you have higher order. So the complexity increases with the order. And then you have an axis. Even chemistry, they use an axis, just an chord. It's just called an axis. So then you order of the reaction. And these are all well known in the chemistry. And then you can say, okay, you're creating, for example, ethane or something, you need to go through many step process. First of all, the carbon combines with hydrogen and then something, then, you know, our cell mechanism, even calcium carbonate and certain inorganic substances need more than one process, one step, like forming calcite or releasing energy from hydrogen, gas, All these are many of them are multi-step processes. And so the order of the reaction is more than one. It could be 2, 3, and 4 even. So if there are more than 2 steps. So I think that's how, so if it interacts, they're interacting, the order will automatically go up. So the complexity goes up as the order goes up. So that way, eventually that creates the life forms, the trees or animals and things like that in certain parts. See, that's why Earth, we don't know. There could be more than one place. I believe there could be other places where the life forms, aliens could be there. I don't rule out that. But as we know that it's very rare. Goldilocks zone or whatever, the Earth has that special condition, geocentric. So it created all this stuff. Now we could have come from other place. We could all be aliens coming from other place, coming to Earth. It's quite possible. But whatever it is, it created oceans. You have to create many things. It has to create rocks to protect the internal structure, which is nuclear in some sense, the internal core. And then the rocks will create that. And then from the rocks, volcanoes and everything, it creates that sea and water and everything. And then it creates the atmosphere. We have oxygen and everything. And from that atmosphere, we have the trees and everything forming with the photosynthesis. And then the animals form the other side, conjugate side. And the animals use the oxygen, and then the trees use the carbon dioxide. They form that cycle that will create sustenance of the life system. So that way, Earth started sustaining the life system. It goes through, like we are born and we die and all that. So it is a continuous process that's going on, even on Earth. That's the way we think the universe is in some ways, many ways. It is a reflection of that, the process of the universe.
Yeah,
So,
everything in the universe is circulation, cycling.
Circulation, yeah. Feedback. I believe in feedback circuit mechanism. So it's a feedback. Feedback is when you have the circulation and the error signal creates. The error signal feeds back into the input side, and then it changes. So continuously it changes until the error becomes 0, then becomes stable. So that's how we get a stable thing. So the growth occurs continuously with the feedback mechanism. Like cells, even our cells may be working like that. That it creates such that that whole thing flows until the error signal becomes 0. So then it stabilizes, forms a stable system or cell or whatever. So like that, it builds up. Then they connect with each other because of the your surface energy and tension, surface tension, your surface free energy, volume free energy. So then they can combine together. So you can explain all that on that basis, how our cells build up to produce organs, and the organs create the whole thing. And on the other side, you have the skeletons formed from the calcium, some calcium carbonate or something like that. And by etching process or leaching process, it creates a small pore in the skeleton system, and that creates the process by which the blood can flow and all that. So you can explain a lot of those things, the whole dynamics, and your capillary system essentially, which goes against the gravity. Capillary, if you have capillary thing, can go against the gravity. It has if we calculate that, we know very simple calculation, and we can also create a capillary tube, and the water or thing rises in that against the thing because it has a high potential. There's a potential difference that pulls it. against the gravity. So it can overcome the gravity. So you have all these system that's created by nature. So if you study them closely, I mean, a lot of the physics is based on that. And also you have anomalous expansion. So ice is lighter, it's also solid, but it's lighter than water. It's in the 4 degrees centigrade. So again, that floats and protects the water underneath. So the nature has created all this complex mechanism, right, to sustain that. And you cannot think of a highly complex system just by from one big bang, one place it creates. It cannot be that complex. So the only way you can express the complexity is that different places you have these, and they form and they interact with each other. And then when in the interaction, the galaxies probably come together. Even galaxies could have hit each other, and they create a common place. And that common place is mighty complex. The complexity increases. And this complexity allows, like you said, could be even from energy, quantum wells, things like that. Wall creates, and that wall could form like quantum well, and they have specific property of energy and things like that. And so you can create a lot of complex things. You have Casimir effect, different things. So it can have a lot of different types of effect, which contributes to the complexity of the whole thing. And that complexity is very important to understand about the life system as well, inorganic and organic system of the nature, how the environment is formed, how the objects are formed in the environment, and then how they move in that environment. If you think about all of that, it's highly complex. So there has to be a minimum level of complexity. That's what I'm saying. Although as a universe, we see telescope that is uniform. They look like two-dimensional, right? But they have small fluctuation. So I believe in the carrier wave and the modulated wave, like radio waves, right? They have carrier wave, but what carries is the modulated wave. So like a radio signal we get is the carrier wave. But when I talk, for example, I modulate that wave is modulated and it travels, the modulated wave travels. So the superfluid is like the carrier wave, but the distorted thing will be like a modulated thing that creates that evaporation and all that. And then you have that local things which creates the hole that creates the gravity. And this process then, because once it starts, it's like feedback mechanism. It's like from a circuit, and it continuously feeds itself, and increases. So you can explain very nicely, I think, a lot of things, based on that.
Yeah.
So it's very interesting.
Yeah, the topic is very wide, very deep.
Yes.
So normally, when do you finish this section?
Yeah, you can almost finish now, because I don't know what's happening with Christopher. We can actually end it now. Next week, if you are able to come, that will be great. I'm going to present about, were you able to watch the history of physics? Other episodes? In the YouTube, it is there.
Okay, thank you.
Yeah. So then I will present the 8th episode. Now we are up to 8th. We are going to up to 10th, but this year up to 8th episode. The next week I will do that. And after that, we can discuss that. We discuss that. Christopher is there in all the time, but then you can also join us. And then, a very simple way of looking how the physics progressed through the history from Galileo onwards. That's what it. Very simple. Not too much math. So then, next year we'll do 9 and 10. So I hope to see you next week, Benzong. Have a nice week.
Okay. Have a nice week.
Okay. Thank you.
Right.